has ensured regular daylight and natural ventilation. Should I continue? Natural daylight and ventilation in all the occupable rooms. The shaded courtyards and vegetation buffer has reduced the ambient temperature by 2 to 4%. Now, the double skin windows have also ensured a air cavity that has reduced the direct solar gain. And the moisture buffering and insulation has reduced the relative indoor humidity by within the comfortable ranges. Now, in order to deal with the air quality, we have used reduced VOC materials like lime, earth, mycelium, and timber, and we have achieved 4 to 5 ACH using these. Trinkle vents have been introduced to allow controlled and continuous airflow into the rooms, even when the windows are closed. Now, with the SDI analysis, we have achieved 70 to 75% luminosity and decrease the annual operative temperature by 3 to 5 degrees Celsius. Now, well-being for us was not just limited to the thermal comfort; it extended beyond with mental and social well-being. Now, the open courtyards and shaded spaces have been introduced in order to help the community have help the community have some interactive spaces during the disaster time, and also it will help the students to have interactions and valuable educational uh, feedback during those times. Now, for the resilience, going ahead with the resilience. Now, sorry. The four major potential risks that we dealt with were composite climate, high rainfall, soil erosion, and debris runoff. Now, the major disaster that that the people of Solon face are landslides and flash floods, which have had an increased impact over the last few years. Uh, Water absorptive plants, site grading, step landscape, and permeable hardscapes have been introduced in order to decrease soil erosion and uh, reduce the reduce the speed of the debris runoff. Another disaster we looked for was earthquake. Seismic resistant techniques, which have been long used in the regions of the Solan district in Himachal, like Dhaji Diwari and Katkuni, have been introduced in order to achieve seismic resilience. Now, heat stress has been one of the major concerns that has emerged during the modern times. Shaded courtyards, ramps with deep overhangs, high thermal mass walls have been introduced in order to reduce the temperature by 3 to 5 degrees Celsius. Resilience was also included in the resources and for the community. Energy and water resilience had more than 60 hours of autonomy during the disastrous times. Thank you.
To maximize, to maximize the sustainability of the building, we use three main contests: energy performance, water performance, and embodied carbon. In energy performance, we use and passive strategies like shading overhangs, calistrate roofs, courtyard and landscape, cross and stack ventilation, low U value, which which reduce the energy consumption by 28%. And now we reduce the energy consumption by building envelope. In this we use CSB and mycelium insulation, and in by this we reduce the energy consumption by 18%. And we use the energy efficient fixtures. From this we use the lighting, Philips usual LED patterns and the BLDC fan. From this we reduce the energy consumption by 10%. Now with the use the renewable energy, from this we reduce the energy consumption by 6%. And in this we off grid the 72 hours in 3 days. or in this we base case and proposed case. And in water performance, 1 lakh water tank, 1 lakh storage tank हो रहा है. And the is grey water is reused and treated and cleaned in the hand washing and cleaning. Or we use the some reduction by dual flush toilet, and we you reduce the water consumption by waterless urinals, dual flush toilets, etc. By embodied carbon, we reduce the 92% and we use some materials, straw well infill, mycelium insulation, clean red timber, slate roof tile, CSB, stone. And by the floor, we reduce the 79%, and by roof, we reduce the 96.2%, and by the wall, we reduce 98.5%, and by the structure 61.6%, and by fenestration 94%, and the overall embodied carbon reduction is 92%.
We are catering to the community by making our design affordable and replicable. Um, we have reduced the baseline cost from 80.4 million to 68.4 million rupees, saving 12 million rupees. The major saving comes from the internal works MEP system and the reduction in interest during construction. Uh, the life cycle cost, as we can see, uh, the proposed case of 25 years, the graph is flat, indicating that low cost for maintenance and operation of the building, and the saving increase in 25 years. These are the strategies which we use to make our design affordable, and the solar panels become economical by using 70% subsidy by government schemes. In collaborative innovation, we have collaborated with people of different backgrounds and with the authorities, government authorities, and the features of our building that we have collaborated are by using the vernacular techniques, transformative furniture, um, and the ramps. We have collaborated with the uh, we have collaborated with DMR and made mycelium on site, and also made the active edges of our site.
Now, why should EDMA, the local authorities, school, or communities invest in this solution instead of a normal shelter or a normal school? The value proposition of Arohan. The value proposition of Arohan lies in transforming a typically underutilized emergency facility into an active community asset. Now, for the users of the school, uh, it has created a high level of employment and job security within this faculty, and also it has increased modern vocational training. It has embraced local cultures by introducing those vocational training efforts. Now, for the disaster affected people, the extended stay facility has been one of the major concerns. We have given a stay of up to 2 months during the disastrous times, and also provided with livelihood support using kettle sheds, etc. Now, for the community, vernacular materials, familiarity with the design has been introduced. Now, ultimately, Arohan creates value at three levels: value for an individual through safe and healthy spaces, value for the community through education and disaster preparedness, and value for the institutions through a cost effective, replicable, and resilient development model. Now, to sum it all up, thank you.
Okay. Thank you, team. That was an insightful presentation. Let's hear the jury's comments and take questions from them. Piyush, I'll start with you.
from non-terraced areas, because when you're looking at softscape and hardscape, the kind of debris flow, the kind of impurities that may become part of this water is very high, very different from the kind of control you have on roofscape. So, from that perspective, we had also given you some comments even in the last round. And if you could throw some light on how you've tried to address them or how you've tried to deal with them. Should we do the questions first and then get them to answer?
So to answer the carbon question, the use of various materials like mycelium infill, it was studied that mycelium infill can be used in place of many insulation boards. Like we could have used sheep wool and other insulation boards, but we switched to mycelium because Solan is the mushroom capital of India, and the availability of mycelium there and the research institutes present there. So mycelium could be very effectively used as insulation in walls and in roofs, hence mycelium for the assembly. And for the slab assembly and other parts, we have used CSEB and timber, which go well together, as in the CSEB was majorly used for the structural part to make the assembly structural as well as reducing the U value. And to answer the next question about rainwater harvesting, yeah, the roofs were used for the rainwater harvesting, the slopes and the gutters, taking it down to the rainwater harvesting pit. For the soft-scaped and the hard-scaped area, we have used absorbent materials in the pavement so that they can absorb the water and to replenish the groundwater, while the green areas of the ground were used were done with grass that could easily let the water through. For further on this thing, we have used, like, for the irrigation, to reduce the water used in irrigation, we have used plants that use less water sometimes during the disaster times, especially to save water in that sense. Yeah.
Hi team, congratulations to making it to finals.
Thank you, ma'am.
Okay, I wanted to know that you mentioned a couple of times that the shelter timelines may be around 2 months.
Yeah.
How have you arrived on 2 months, and what are the pros and cons if we extend it by 6 months or 8 months or maybe 1 year? That's question number one. And question number two is, like, in terms of communities, resilience, and shelters, water availability becomes one of the very important part. How do we ensure that water availability not only for 2 months, 6 months, 8 months down the line?
Hmm.
So if you could just please highlight that.
So yeah, so the to answer the first question of using the time period of 2 months, during our site visits, we did understand the durations that the families, like as we said, the on our site where there were temporary shelters that were being used currently by the families that were affected. So we did understand the timeline they needed to rebuild their houses during that time and what the government provides for them to do that. According to that calculations, we were sure that during a period of 2 months, they could stay here while their houses and their, the homes are being rebuilt, the villages are being rebuilt, so they can shift back
to their homes. So the shelter is just as a temporary solution when they are not able to live in their homes. It is not a permanent solution for them to just shift here. So hence the timeline of 2 months. And furthermore, the project partner, the DDMA, suggested this timeline for the shelter use. And to answer the next question, which was about, I'm sorry, I missed it, water availability during the disaster times. So we have firstly provided two types of tanks. There's an overhead tank for the daily use of water, placed above the washrooms and the kitchen areas. While there's an underground water tank also made, which is basically made with the purpose of storing water during the disaster times. The water stored during the normal regular times by the rainwater harvesting is stored in those tanks and used when there is a need for water to be used. Otherwise, we can also, do have a provision that we might end up taking water from the municipality for some period, but we are sure to give them back during the heavy rainfall times when we are getting those water numbers back. Yeah.
Hi, congratulations for making it
Thank you, sir.
and all the best. Well, similar comments which were noted in the the last feedbacks given to you.
Yeah.
One is about the complexity of the number of materials that you used. It would be good. It's okay to use, and I think it's important to begin to understand. But I think it's useful when you use new materials how you are actually, because you're talking of katkuni. On one side, you're talking of katkuni, which is basically, and you show a lot of horizontal members sitting on each other, and then you're talking of mycelium as walls. So we don't know where it is the katkuni and where it is the mycelium. So in that sense, that's something that you would want to probably clarify. And maybe on certain directions you need better insulation. On certain directions you may not need so much insulation. So that clarity would also be useful. Right now it's seen as a number game, and you kind of, because you are looking at reducing your numbers, so you put it all around, so the overall average UV and U values and all of those reduce. So I think in terms of design, you really want to kind of make that more specific.
Sure. So for the part that
That's okay. Go ahead.
yeah, well, if you were supposed to come.
No, go ahead.
So for the mycelium boards being used, as you can see in the wall assembly, we have horizontal bands. Hence, the mycelium boards can be cut in rectangular pieces and used between those bands as an infill, along with air cavity infill. So that is how the bands are being used in the horizontal bands, the construction wise. And the point that we did not alter the wall assembly as per the different directions. Yes, we did keep all the four walls like for a block. We have kept the same assembly throughout, and that makes a good point that we should have considered it. And probably we just switched, like kept it to the numbers, keeping it low, so we can work more on that.
Yeah, I mean, your rainwater tank is 1 lakh liters, but the harvested is 35 lakhs. So I think that was also pointed out in the feedback. So you want to kind of look into that, because I think that also the clarity that what is harvested and what is recharged. Normally you would harvest only the terrace, where it's basically clean surfaces, easier to manage, and you would recharge the groundwater which falls on the ground. And one of the important things that you must do is when you're doing a study of a site, you obviously, water is not just falling on your side, especially in a hill. It's also coming from
Down the runoff.
somewhere else also. So a nice map of a location which shows the various water flows across and around your site, and how you're also tackling that, because the disaster is actually going to come from outside.
Yeah.
And it's going to affect you. So how have you taken care of that? It would have also kind of shown a little understanding of where you are and how you're managing. So that's, I'll rest my case. There are many comments, but I think you've already got the feedback.
Okay. So for the runoff and that point, we did consult with a team member that was in the landslide disaster management and our faculty advisor, and we realized that our site lies on the convex contours, and what the natural drainage patterns follow the concave patterns. So hence the water will naturally flow through the surroundings of the site and not directly coming. But still, for an extra added security, we have added the multipurpose hall as per the zoning was added on the topmost part, which is a bulky mass with a higher plinth than the rest of the building, to stop any debris that might come to enter the main side, and it would just run off from the two sides. That was how we thought of dealing with the debris flow and the runoff. Thank you.
Thank you, jury members. Thank you, team. Naraya.
Thank you, ma'am.
Let's take 5 minutes and get ready for the next presentation. They have worked on an extension of an existing resort in Port Blair at South Andaman Island. Team, you will have 20 minutes to present your work to the jury. At 15 minutes, I'll ring a signal like this. You have 21st minute, which means at 20 minutes, I'll stop you and ask to end your presentation. After that, we will have 10 minutes for a Q&A session. Please keep your answers direct and to the point. Okay, team, the stage is yours. Good luck.
Good morning, everyone. My name is Rida Salim Sheikh. I am from Team Nirantara, and on behalf of Team Nirantara, I welcome you to Hornbill Nest 2.0 Resort, a community resilience shelter that was built inside a working resort in Andaman and Nicobar Islands. Now, first, before I start talking about it, let us try to understand why this project exists. So our resort was in collaboration with ANITCO, which is a government-led body. So basically, our resort already sits in an intersection between tourism place as well as public service. So it is an already existing community resilience shelter. So what Team Nirantara was asked to do was, to create its next chapter. We were asked to design a series of buildings, especially keeping under consideration the banquet space, which is the main CRS space, which houses around 600 people. Now let us look at how this one building that serves 600 tourists today also serves 600 survivors tomorrow. Now before I start, I would like to talk about the site a bit. So why exactly did we go for Andaman and Nicobar Islands? So if you think about it, the Andaman and Nicobar Islands, although they are a part of India, they are highly neglected in terms of CRS. There has not been enough design strategies or implementations that have been made in Port Blair or anywhere across Andaman, especially considering that these islands face three major hazards, from the seismic zone 5 to cyclone, and also having an entire coastline with history of tsunamis. We thought that we should look at the islands. Why? Because the islands are also a part of India. Now, let us also talk a bit about the community. The community consists of 1.3 lakh urban population, because we are catering to Port Blair, which is actually a city, and also most of the people living here are from mainland. Other than that, let's talk a bit about the climate as well. The climate in Port Blair, also it is also known as Sri Vijayapuram right now, is warm and humid. It has high humidity values, which is 80 to 90%, and heavy monsoon rainfall, high cyclone and flood risk due to strong southwest and northeast winds. Seismically active zone, which is zone 5, and we have a lot of small frequent earthquakes. Problem statement.
Our presentation opens with a voice, Geeta, a resort staff member and local resident. Her story captures the problem better than any statistic. When a tremor struck, people ran to the resort, but it was not ready. There was overcrowding, confusion, no clear pathways, no organized spaces. The resort had capacity but not preparedness. Hornbill Nest 2.0 is the answer to Geeta's experience. Today, the resort is designed so that when the earth shakes, people arrive at a place that is ready for them.
Now let us look at our goals and also their solutions in brief. So our major goal for this project was that it is a tourism spot. So we need to attract tourists, because that is what keeps the CRS space running. That is what funds its entire resort functioning. So firstly, we focused on tourism attraction, and then we focused on resilience to make sure that our structure is resilient enough to handle these three different disasters at once. Also, this is just a brief introduction of the team. And these are our project goals. We won't be going at them at one single term at a time, because in a really good design, our project goals or anyone's project goals are never isolated. They come together. So let us look at the design strategies. Now, this master plan is not just a site plan. Every single thing that you see on this master plan has been designed by keeping certain things in mind. So firstly, we'll start with the staggered placement over here. As you can see, the staggered placement ensures that the cyclone winds are broken down. So in a way, the resort is actually defending itself on its own. And secondly, we see that in the banquet space, I don't know if this works. Okay. Okay, we see that in the banquet space, we have put an earth berm in the south and west side. This is to ensure that, the thermal comfort has been maintained throughout, which is a difference of 4 to 5 degrees Celsius. And also, if you can see the placement, we have ensured to keep the banquet space, which is the CRS structure, on the highest point, considering that the coastline has a history of tsunami as well as floods. Moving on.
Coming to the form development, it is not just an arrangement of blocks, it is a wind management strategy. The earth berm is one of the project's most elegant design, a passive, material efficient intervention that reduces the wind load on the structure, also cuts down the HVAC load, and integrates the building with the landscape. So the building is not fighting with the terrain, but it makes it one. The vault roof is not just a form for aesthetics, but it improves the load distribution under the innovation, under the seismic action and also the cyclone winds. Next.
Now we will be talking about the CRS space in detail. So this is the CRS space during the normal working times. We have two parts of in it where two events can be held at the same time. We have the altar which faces the sea, considering its occasion and its context towards the site and the ocean. We have made sure that the altar faces the ocean and has a nice view of it. And also there's a banquet space where events can be held, and the washrooms are also designed as per both the 4-star resort regulations as well as the CRS regulations. And we also have an HVAC, because since it's a 4-star resort, we have to ensure that there is an HVAC during the functioning of the banquet hall. But however, during the times of disaster, we don't really need to depend on the HVAC entirely, because we have provided an earth berm that maintains temperatures inside. Other than that, during the CRS, this is what exactly is happening. Here's how the transition happens. So our lobby acts as a triad zone. This is where all of them are checked, see if there are any casualties, and we divide the survivors in two different parts. The altar houses men, whereas the banquet space houses both women as well as children. I've already mentioned that the toilets are as per the CRS guidelines. So we have ample of them. And also we have located our banquet in such a way that it is in very close proximity to the back of house of the restaurant. So it ensures that the food is catered on time. No one really has to walk long ways inside the resort, because it is a huge site. It is 22 acres. And the furniture is also modular, so it runs on a 45-minute protocol where you can open the furniture and fix it throughout the banquet space.
Coming to innovative materials, every material was chosen for a reason. Firstly, I'll address the banquet roof. The banquet roof is a layered assembly of ferrocement and steel ribbed arches at the top and a coconut husk fiber for acoustics at the bottom, which is covered with the bamboo battens. It handles the cyclone winds. It also handles acoustics and insulation. The wall uses the hemp as its core. This material, as it evolves and cures, it absorbs the carbon. As well as the floor is finished with terracotta tiles. The EAF steel columns that we are using are base isolated, and hence they reduce the embodied carbon to just 1.74 kg CO2 levels per square meter. And we get a 55% reduction in the seismic action also.
Moving to the innovations that make this project distinct. We have a modular jute weave teak chair, which will be used in the banquet for seating purposes and reconfigured during CRS times into shelter furniture. Our openings use bamboo lured blades with low E double glazing, controlling heat and glare without mechanical systems. We have used laterite and chicken mesh wall. We took a solid wall and made it breathable. It diffuses wind pressure while allowing airflow through. A simple local technique solving a complex coastal problem. The yoga deck roof is semicircular, engineered so that rainwater drains to the periphery instantly, preventing any stagnation in a high rainfall zone.
Coming to resilience, this is where the numbers matter most in CRS. So what we have done to keep the structure resilient is that first of all we had a loose stone compound which acts as the first windbreaker for the prevailing southwest winds. Also the rooms are sitting on silts which are of pier foundation, so they are safe from the floods and also they are safe from the seismic activity. We also use native trees like Alexandrian rolling, Indian almond, and also Andaman wild mango as a second windbreaker, so that the wind that reaches the building is actually safe. And then the structure, which has the aerodynamic design, it deflects the wind in all the direction. And a vaulted roof improves the load distribution. Coming to the StatPro, we did the StatPro analysis and we identified the beam and column placements that were required to match the load at the worst case scenario. At the affordability, you can see the chart of the project summary that we have done, and the capex of the project is 1.32 lakhs per square meter as a proposed design. While we did a SOR based baseline study because our was not able to provide us with a baseline, so that came to 1.39 lakhs per square meter, and the OPEX running cost was 80 million per year.
Hornbill Nest 2.2 is a cooling only building. Because it's hot and humid, we do not require any heating. The dominant load is latent and not sensible, so we've paired a centralized HVAC with a dedicated outdoor air system to manage dehumidification independently of temperature control. Now we're not using mechanical cooling all the time. We're using a BMS system to manage it only during hours of discomfort. Next. Our power hierarchy is solar first. Solar panels generate electricity for daily use. Thereafter, any excess solar energy is stored in a BESS system, and diesel is there as a backup only in case of extended failures. But on calculation, it has been found that we may not require it. We went from a base case of 1,85,542 kilowatt hour per year down to a proposed case of 76,352 kilowatt hour per year. That's a 58% reduction in our energy consumption. The key design here from our shoebox modeling was that shading drives energy performance more than the glazing ratio does. The iterative shoebox is what led to our revolution of the final banquet design. We follow a solar-first hybrid energy system, and we're proposing a Tata Power solar panel, a 540 peak monocrystalline PERC module at 21.29 efficiency. This is also MNRE approved. Combining rooftop arrays and solar parking shelters, we are achieving an annual generation of approximately 6,82,524 kilowatts hour. We've built in provision for future expansion towards the south so that we'll be able to reduce our dependence on Port Blair's vulnerable grid. The suggested EPI benchmark for the CRS in hot and humid climates as per SDI was 55 kilowatt hour per square meter per year. Our own target to meet Super ECBC was 41.8. We've achieved 38.45 and we've beat our own target by 16.7%. Our water strategy focuses on the transition from a standard 4-star resort to our sustainable model. The baseline for the standard 4-star resort is 320 LPCD. We've reduced that to 200 in our proposed case, which is a 37.5% reduction in demand from 292,160 liters per day down to 182,600 liters per day. This has been done through the proposal of water efficient fixtures. The fixtures alone account for 93.15 liters per day in savings, with behavioral and system changes contributing to another 26.85. And critically, this isn't just about reducing our demand, it's net zero water. 100% of non-potable demand is met through on-site recycling, and our STP treats the remaining of black water combined with grey water reuse. Total rainwater harvested annually is 33,670.618 kiloliters per year, which makes us net positive. All the rainwater harvesting is done through the roof surface drainage, and whatever is the surface runoff through hard water is sent to recharge pits, so to help in groundwater recharge.
Coming to embodied carbon, we have actually used multiple materials, a combination of a lot. You can also see a roof assembly over here, which is actually a 9-layer roof assembly consisting of ferrocement, materials like coconut coir and bamboo battens and more. So our carbon reduction strategies were basically using bio-based carbon negative materials, material substitution for, we just wanted to create something that is not an RCC, traditional RCC structure in Port Blair. We have also reduced the cement use drastically because we have used bamboo in most of our roofings, and we have tried to use CESB wherever possible. And we have designed for disassembly and longevity. Local material has been sourced, which has reduced a lot of embodied carbon that would have been caused due to the transport between the mainland and the islands.
For the banquet hall, we ran 2 scenarios to validate our ventilation strategy. Normal operation stabilizes 665 ppm, which is within ASHRAE limits. In cyclone mode, with outside air fully shut, the CO2 does cross the limit very fast. So standard HVAC alone is not enough. Our response, a storm-rated ERV at the envelope and a CO2 scrubber in the HU room, both BMS triggered at 800 ppm. Next. Our well-being design operates on 2 tracks. Physically, we provide an open yoga deck and rely on thermal comfort delivered through a combination of HVAC, natural sunlight, anti-glare treatment, and natural ventilation.
We have 7 types of bins in our resort: organic food waste, recyclable, non-recyclable, hazardous and biomedical waste, sanitary and medical waste, small dual compartment bins, which we use in the rooms. We have 3 waste collection points on our site. Main service collection point, which is at the back of house, secondary collection point, which is near parking area, and emergency collection point near the banquet. Outdoor bins have a weatherproof design. They are fabricated from recycled plastic slats or heavy gauge steel to withstand harsh conditions, including extreme heat and high humidity, ensuring year-round operational integrity. We have calculated the number of bins on basis of number of users and the need of the space. Coming to the value proposition. Our project Nirantara creates value for 4 key stakeholders: community, staff, visitors, and project partner. For the community, we provide job opportunities through furniture assembling, access to essential resources like food, water, and medical support, and improved infrastructure. The banquet hall also doubles as a disaster shelter. For the staff, the design ensures a safe working environment, recreational spaces, career growth through skill building, and a cyclone resilient structure they can trust. Our smart app, which is right in front of you, reduces the workload of manual work entirely. The moment there is an issue, staff gets an instant alert. Sensors automatically switch lights on and off based on the time of the day. During the cyclone, a wind sensor at the reception detects the emergency, and the lighting, fire system, everything activates automatically. And the building becomes ready for refugees without anyone having to manually intervene. One app does the work of 100 staff. We have distributed responsibilities so no one is overburdened.
For visitors, the Andaman is already a fantastic destination, but the rooms are made sure that they are oriented to get a very nice sea view, and all the other spaces are designed so that you are getting the best view that is possible. And the stack and venturi effect that we have included, what it means for the design, what it means for the clients is they are getting the most fresh air that is possible, which is also naturally cool. And then for the project partner, yes, the cost is high, but when you're giving a premium experience, which is a 4-star, then it justifies. Plus, the running cost is almost nil because the water is 100% clean for all the non-potable users, and the energy is also met on site. Moving to what the design delivers, energy consumption is reduced by 57%, net positive in energy. So basically, if there was another resort, we could give them electricity in all terms, right? And then the banquet hall has an aerodynamic form which doesn't just fight the wind, but it also provides an aesthetic, and also it covers 600 people at the CRS crisis.
100% of our energy needs are met on the site. On carbon, we don't just reduce emissions, we sequester more than we produce, a full 200% reduction. Water consumption drops by 37.5%, and our cost comes in at 1.32 lakh per square meter. On health and comfort, we achieve 53% SDA, 100% comfort hours through passive strategies. All of this is backed by super ECBC compliance, GRIHA certification for water, and 90% waste diversion. It's not just a good building, it's a good business. Thank you.
Thank you, team. You have finished well in time. Now let's hear the comments from the jury members. Yes, Piyush, you must start. Or Surya, sir, you must start.
Hi, well done. One major thing that comes to mind, because the main shelter is that banquet hall. So fundamentally, in disasters, you're going to be there, and in disasters, the power would be one thing that may be in question. Even how much of a backup you may have, could be a question about it. So would that building need some kind of breakout spaces, better quality ventilation? Because it's quite like a box. If you see, and it's a humid area,
Yes.
Andaman, Nicobar, those parts are very humid. So good cross ventilation, fundamentally, basically, you're allowing good cross ventilation. So obviously, if you want to do something like that in this kind of a building, you may need breakout spaces. A lot of the spaces in that building, if you notice, whether it's the toilets, whether they're quite dark, they actually do not have naturally even light. Wind is one aspect, even light is a problem. That's the kind of opening. So that would be a point that was also commented in the this thing. So have you been able to look at that and
Actually, we have gone through that. What we have kept under consideration is that if we had opted for cross ventilation over here, since we are placing the banquet hall on top of an hill, so it's a conduit site, we are placing the banquet hall on top of this hill, and if we were placing it in such a way without that earth berm, then the wind would not deflect over the building. So what we wanted to ensure is that the wind moves seamlessly around and about the building, which is why we kept that earth berm. And a plus point of it was that it was also reducing the temperatures inside. Cross ventilation, however, would be an issue over there. So we do have HVAC, and for as for energy that you mentioned, sir, the our entire resort can function off grid for, I think, a really long period of time, because it generates 900% more energy than required. So on an every single day basis, we are giving back to the community constantly. So if in case a situation arises that there's an entire power blackout, the resort can sustain not only itself but also the community around it. So we don't have to worry about the energy aspect, since it has been taken care by solar entirely.
general comment on the design overall? Since it's a sloping site and it's going towards the ocean and there's a lot of rain in these parts, could you have looked at small berms, just like the way you looked at the berm to break the wind along the downslope, so that you could stop the water instead of the erosion of the soil when the water goes down to as a design proposition, which then creates the smaller units. So you take the larger idea into the smaller aspects. Did that come across as a possibility?
Actually, if you look at the master plan, just a minute. Throughout the master plans, we have recharge pits for the rainwater to be harvested. And also, as you mentioned about putting berms, we have this. We have made walls over here towards the sloping sides, which are made up of coarse materials. So not only are these walls breaking the winds which come towards our buildings, but they are also stopping the rain. So we have tried to reduce erosion to a very large level. You can see in the resilience part actually. So here we have this compound wall, which is a loose stone compound wall, which we have used as a landscape windbreaker to reduce the south winds as well as to stop the water. It functions as both. So it works as a barrier.
Congratulations, team, and also congratulations on arriving with this app. which you just showed to us, and I specifically liked the CRS mode on and in auto and manual. I would actually like to know more about it. That how is it functioning, auto and manual thing? Specifically, let's say if in terms of the use of community resilience time, if let's say the rainwater availability is not there, and you're just having the treated water as a alternate water, so how you're going to feed the entire system? And question number two is, like, you have a 22-acre property, right? So
Yes, ma'am.
apart from the roof area, the building footprint, have you thought around the non-roof area, in terms of any solutions coming up with?
We have also taken under account the permeable roads for rainwater harvesting. And as for your first question regarding the app works entirely on based upon sensors. The reason why we came up with this app is because it's a very large site, and no matter how many employees we have in the resort, it's going to be very hard for them to manage. And CRS is it's not just a normal BMS working app. Since it caters towards CRS, people need to be very fast. They need to act on time. So if someone can sit in one single place and handle all of the switches just through sensors, that would make the functioning of our CRS building way more efficient, which is why we came up with this app. And so when it is on CRS auto mode, the entire resort is functioning based upon sensors. We have a wind sensor on top of our reception, which notes down the how fast the wind speed is moving, so that it can alert you if there is a chance of a cyclone happening. There are also multiple sensors located around and across the site to give you alerts on a daily basis, like on live basis, that if something is not working, if there is a leak somewhere. And so the entire and you were talking about how exactly the water is going to be reused. How is the reused water is going to be?
Yeah, I was
Yeah.
talking about being very specific. In this time, so you showed it as a net zero property, right?
Yes.
22 acres, a lot of area under non-roof area, right? And in that, when I saw your water balance, you had couple of categories into it,
Yes.
and saying that alternate water coming mostly from rainwater or STP.
Yes.
Right? So let's say in case if rainwater availability is not there at this time, so you're just depending on the treated water, STP treated water as an alternate water, or you have any other alternate water sources?
Actually, ma'am, we are using the STP treated water throughout for landscape because the resort has a lot of trees.
Okay.
So, in case that there is a shortage of water, which which is very not likely to happen considering that we have 3,500 of annual rainfall. But still, we can't use the municipal water because the municipal water lines are available. And even if that is not possible, then STP treated water will be enough for only the banquet space, but not the entire resort's functioning.
Ma'am, in case of the 6 dry months, in case there's no rain, we can take 100 kiloliters per year from the municipality, and then when there is rain, we'll be able to give it back to the community.
Okay.
Yeah, thanks. So I have a question which is probably very basic here, is that while you're saying that there's a community resilience shelter, I don't really see the community. What I mean by that is that I don't get a sense of who are the people who will be brought in here or who are the people who will come here. So, you can't really have a community resilience shelter just because your client wants to have a community resilience shelter on their campus. So it's not just a design solution. There has to be some sense of who is this community, what do they normally do, why will they come here? And then, of course, if you start looking at the design, it may work as a banquet hall. I have some doubts about that, even from a structural perspective. You've got a irregular form, and you're saying it's a vaulted roof. The kind of sections you've used there are 9 materials in it, and so on. So that's probably a different discussion. But how will this actually work? So it's, see, at a concept level, it's fine to say there's tirage and then there's a separation and there are enough number of toilets. But how will it work unless there is no engagement with the community, understanding what their needs are, what the special requirements are? And then there's this whole issue of, it's an HVAC based system. So what happens in extended stay periods in these spaces? So maybe too many ideas here, but if you could just respond to this whole, where is the community?
So to respond to where exactly the community is, so our project is located on the Cooves Road. So it is a major prime location in Port Blair. And if you see in and around the site, we have a lot of fishermen living there, and there is a university also which is functioning over there. So there is enough traffic. And since it is located in Port Blair, and Port Blair has only 6 major CRS spaces, which and Hornbill Nest Resort, the already existing resort, is one of the CRS spaces. So the community has been divided based upon zones by the government itself. So the disaster management authority of Andaman and Nicobar works alongside ANITCO and other partnered institutions of the government to divide their particular spaces in terms of zones, where our zone caters to the fishermen, the students of the medical college that is located around it, and also a few small dwellings which are located around the site. So that is the community that we are majorly looking at right now.
Hello. Yeah. Thank you, jury members. Thank you, team Nirantara.
Thank you.
We will be taking a short 15-minute tea break, for which the tea is been served outside. Folks online, I request you to stay tuned with us and support the upcoming teams. Thank you.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through.
Hello. Yes. So, welcome back to the presentations for the Community Resilience Shelter. Our third presentation is from Team Amara. They have worked on a climate responsive community shelter in Bhuj, Gujarat. Team, you will have 20 minutes to present your work to the jury. At 15 minutes, I'll ring a signal like this. You won't have 21st minute, which means at 20 minutes, I'll stop you and ask you to end your presentation. After that, we will have 10 minutes Q&A session. Please keep your answers direct and to the point. Okay, team, the stage is yours. Good luck.
Good morning, everyone present here. Myself, Ikshita.
I'm Yashita.
I'm Akshit. I'm Surya Narayan.
We're students from BMS College of Architecture, Design and Planning and BMS College of Engineering. We are here to present our project Together at 45, a community resilient shelter in Bhuj. Most disasters have a moment, a tremor, a landfall, or a surge of water, whereas heat has none. It accumulates degree by degree, hour by hour, until something gives, and that's what makes it so hard to ignore. We have built civilizations in earthquake zones, we have built cities in floodplains, we have always found a way to design against nature's forces. But heat is different. It is everywhere, it is increasing, and for the first time in human history, we are approaching temperatures that a healthy human body simply cannot survive. We started this project in December 2025, and the world has spent the month since then making our case for us. In April this year, just weeks ago, all of the 50 world's hottest cities were in India. All 50 in India with an average temperature of 44.7 degrees. CNN called it among the harshest heat events on record, even for April, which is not even peak summer. The answer to this crisis cannot only be mitigation. We know we need to change how we build, how we consume, how we live, and that change is coming. But most people cannot afford to wait for policy to catch up. So alongside the long work of prevention, we need buildings that meet people where they are right now. And that is the line our project walks. A building that protects lives today while being built in a way that doesn't cost the earth tomorrow. And it was through our collaboration with Aina, Artisans in Architecture, a part of Hunarshala, who have been working on ground in Kutch, that we found our project. Bhuj experiences temperatures exceeding 45 degrees Celsius, making it one of India's most heat-prone urban regions. And the people who are most affected are not sitting in air-conditioned offices. They are daily wage laborers, street vendors, waste pickers. And Aina has been working with these communities for years, and they gave us something that no research paper could. They gave us direct access to the people of Madhapara. We went there, we sat with them, we listened, and what we heard was not just about the heat. We learned that heat impacts far more than physical health. It also threatens livelihood by forcing people to miss work and lose crucial income. We also saw how inadequate housing and lack of shade leave many residents prone to extreme temperatures. What was missing was not charity. It was a place, somewhere cool, somewhere safe that belongs to them on their worst days as well as on their every day. This realization shaped everything. Rather than designing a building that activates only during emergencies, we asked the question, can a heat refuge become a year-round community asset? Can it offer protection during crisis and calm during the opportunity during the calm? That became Together at 45, a community resilient shelter designed by us, Team Amara, students of BMS College of Architecture and Engineering, for 225 occupants that transforms according to seasonal needs.
तो उसको बैठना और सोना घर में बहुत मुश्किल हो जाता, तो इसलिए वो ज्यादातर बाहर या पेड़ का सहारा लेते या कुछ कहीं पर बाहर ही बैठते हैं, घर में नहीं बैठ सकते। और दूसरा कि इसमें बीमारियां भी बहुत ज्यादा होती है छोटे बच्चों को और बुजुर्ग लोगों को।
The people you heard are not just describing a single problem. Taking direct quotes, Rama Ben said, she put together money and bought a trampoline, which was much cheaper than a sewing machine. I go out every weekend and let the kids play on it for a little bit of money. And that's how she collected money to put her daughter through a school and college. Akash, a 13-year-old kid, said, I wish we did not have to go so far to attend school, and he wanted somewhere to play in the shade close to home. He did not create these gaps, but it makes every one of them unbearable. And these gaps became our program. Every space in this building traces back to what we learned in Madhapara from the people itself. Our site is in Butch, a 2,400 square meter plot with a permissible built-up area of 2,100 square meters, with ground coverage at 45%. It sits at 100 meters above the sea level in a hot and arid climate zone where temperatures regularly exceed 45 degrees Celsius. The pre-design analysis, our conversations with the people of Butch, told us what the building needed to feel and function and mean. And the answer lay in the Bhunga, a traditional circular dwelling of Kutch that has been solving the same problem for many years. Circular form reduces heat gain. Small controlled openings manage ventilation without mechanical intervention. And the earthen walls act as a thermal mass, and its geometry has proven seismic resilience. So we took these principles and scaled it into a two-story contemporary facility through a thorough zoning strategy. The result is a building that feels culturally familiar to the people. The earthen materiality, the curved edges, the veranda, the woven fenestration panels, and the aesthetic is not imposed from the outside, it grows from the place itself. Zoning of spaces is done so where the climate puts it to best use. The community halls are placed on the north, where it gets the most consistent, gentle sunlight throughout the day. And the conditioned spaces like the healthcare and the recovery room are towards the southern side, where the mechanical cooling it needs is most justified. The ramp runs along the southwest edge of the plan, where it acts as a double wall, acting as a thermal buffer before the harsh sunlight reaches the occupied interior. And between the active zones of community and training on one side sits the central shaded courtyard, which also acts as a seasonal water body. Beyond thermal performance, zoning was also planned with emergency egress in mind. Clear, unobstructed exit paths were provided from every zone of the building during emergency. And critically, every architectural decision feeds directly into the building performance. The curved form reduces heat gain, the split roof drives internal air circulation, the southwest ramp doubles as a double wall acting as a thermal buffer, and the courtyard cools the air before it reaches the other occupied spaces. The form and the systems are not two separate things sitting on one another, but it was designed together from the very scratch. During peak heat months, the building operates as a cooling refuge, healthcare support center, and emergency shelter, along with a training center, learning space, and community hub. So this is one building, two modes that was made for every single day.
The rammed earth walls are not reinforced throughout. The reinforcement is provided at structural locations to resist seismic and lateral forces while minimizing cement and steel usage. Detailed roof drawings and sectional drawings are included, showing the timber trusses anchored to steel beams have also been included that shows the load distribution uniformly through the columns. Considering Bhuj's conditions, the roof tiles are mechanically secured using clips to prevent uplift during high wind conditions. The structure design has been developed in accordance with IS 13920 with certain provisions from IS 1893 for earthquake resistant design. A strip foundation system has been provided to ensure uniform load distribution and controlled settlement of building under seismic events. The proposed steel reinforced lime stabilized rammed earth columns are supported by research from IIT Guwahati and IIT Agartala, demonstrating their suitability as load-bearing members, and they provide improved strength and ductility under seismic forces. Having a compressive strength of 13.5 MPa when compared to an RCC structure of 20 MPa, for a low-rise structure, the rammed earth system provides sufficient load-bearing capacity while significantly reducing embodied carbon, cement consumption, and dependence on energy-intensive materials. Waste is managed through a decentralized system where biodegradable waste is converted into biogas for energy generation, while recyclable and organic waste are segregated at source itself, ensuring that resources are recovered locally and landfill waste is reduced to a minimum.
Innovation in this project was never about introducing something expensive. It was about transforming what the community already had into something that performs. Our key material innovation is the date palm composite board under the guidance of IWSD. So Bhuj generates approximately 22 to 25 kg of dry date palm waste per tree annually, most of which is burnt. So we converted this agricultural waste into insulation panels composed of 70% date palm, 20% bioresin and 10% lime with a thermal conductivity of 0.05 to 0.07 units. Prototyping demonstrated a consistent 3 to 4 degree drop in the indoor temperatures. Aina also asked us to think beyond the new building to the existing housing stock in Madapara that has no insulation, no fenestration strategy, and no passive cooling whatsoever. So we developed retrofitting solutions using the same date palm system, a double wall with hollow roof tiles and a sandwich roof panel that can be applied to existing homes without any demolition. It's simple, local, and replicable. Operationally, the building runs on ambient indirect evaporative cooling, offline earthquake alert systems, real-time thermal monitoring, Jal Rakshak grey water recycling under natural solutions, and biogas generation from solid and cattle waste under Gangotri energy solutions. None of this was imported into the community. All of this was developed from what the community already had. This is our working prototype of the pivot and slide woven fenestration panel, built in collaboration with AK Interiors, where Mr. A. Kumar helped us engineer the sliding and rotating mechanism. The modified roller wheel handles the slide, while a simple metal pin lets each panel pivot independently. Every material here is salvaged or local, leftover wooden scraps for the frame, and a hand-woven agricultural waste mat for the shading surface. It's a practical demonstration of how a traditional shading idea can become a flexible, low-cost window and door system for climate resilience. The date palm fiber material and fenestration was well received by our project partner Aina, and further study to implement it is ongoing. Everything we've described so far, the form, the structure, the systems, exists for one reason, for the people who are going to be staying inside of it. Through rammed earth walls, shaded courtyards, neem vegetation, stack ventilation, overhangs, and evaporative cooling, the shelter maintains thermal comfort for 99.3% of occupied hours, and natural ventilation achieves 3.5 air changes per hour. Indoor temperatures are reduced by up to 4 to 6 degrees compared to the outdoor condition. External and internal CFD analysis validated the building's climate responsive design, improving the cross ventilation, enhancing courtyard cooling, and preventing stagnant air zones even in the most heat prone months. But health here is not just about the temperature. It's about what a cool, safe, dignified space should look like. A person who's not exhausted by the heat can work. A child who's not suffering can learn. And a community that has somewhere to gather can support itself. This building is not just a thermal intervention, it's a form of preventative healthcare embedded into the built environment. We approach the energy in two directions simultaneously, drive demand down as far as passive design allows us, and then meet what remains entirely through renewables. On the demand side, the building envelope does the heavy lifting. Rammed earth walls, a split roof, the double-walled ramp, and the shaded courtyard together reduce the cooling loads to the point where evaporative coolers, not air conditioners, are sufficient even in peak summer months. The EPI has been reduced by 50.8% from baseline, while considering that the coolers run throughout the year, and when considering that the coolers are running only during peak heat months, EPI is reduced up to 57.8%. On the supply side, we have 65 rooftop solar panels with a DC capacity of 35.1 kilowatt. Peak generate 83,000 kilowatt hours annually against a consumption of 73,000, which is net positive, and the surplus is exported to the grid through net metering. Biogas from the cattle shed contributes further, closing the loop on every waste stream that the building generates.
The water cycle follows the same principle as the rest of the building, closing the loop completely. Water is sourced through a combination of municipal supply and rainwater harvesting, reducing dependence on external sources from the outset. Grey water generated from wash basins and showers is treated through a reed-based system, followed by a Jal Rakshak and nanofiltration unit, allowing it to be safely used for toilet flushing, landscape irrigation, and other non-potable applications. Black water is treated through a multi-baffled anaerobic bioreactor, while ultra-low flow fixtures and water-efficient appliances reduce potable water consumption by up to 45% compared to a conventional building. Overall, the building has an annual water demand of approximately 1100 meter cubes, of which nearly 70% is met through rainwater harvesting and recycled grey water. By combining on-site wastewater treatment, groundwater recharge, and efficient water use, the project returns more water to the site than it extracts, achieving a net positive cycle. Instead of simply conserving water, the building actively replenishes local groundwater, making it a resilient solution for a place such as Bhuj, where water scarcity is a critical challenge. We treated the material palette as a design decision, not a specification afterthought. Every major building system, roof, walls, floor, fenestration, structure, was evaluated against a baseline and replaced with a lower carbon alternative locally available in Kutch. Rammed earth walls, PFA stabilized soil blocks, date palm fiber boards in the roof sandwich panel. The fenestration panel is woven from agricultural waste that would otherwise be burned, making it carbon negative at the material level. Total embodied carbon reduced by 80.7% against the baseline, wall emissions down by 82.5%, roof down by 67%. These are not marginal improvements, they are a fundamental rethinking of what a building in this climate should be made of.
Three simultaneous threats: extreme heat, seismic zone 5, and infrastructure failure. We designed against all three. Against heat, 99.3% of working hours are within IMAC thermal comfort range through passive design alone. The building is resilient to heat by its very own form and material used. Against seismic events, reinforced ram shear walls, strip foundation, which shows a lateral sway of 8.48 mm against permissible sway of 30 mm. The Bunga derived form itself contributes to seismic stability. Against infrastructure failure, the solar surplus energy is available during grid outrage. The facility is equipped with water and electrical backup system, which sustains for 72 hours. A risk assessment for 50 degree was performed, which demonstrated that 97% of working hours under thermal comfort range. Resilience that cannot be afforded cannot be adopted. Our proposal achieves a 10.6% in reduction of overall project cost compared to baseline construction through locally sourced materials such as earth, bamboo, and stone, with community participation during construction. The constructability of the project is estimated around 1.5 years. Sweat equity is not a new idea which we introduced. It's what Unashala and Aina have been practicing for years. The project follows the same model where the people of Madhapura are not just end users, but hands who built it. Long-term operational costs are reduced further through net positive solar generation, biogas replacing conventional cooking fuel, reed bed wastewater treatment, and low maintenance natural materials. In a community where average household income is 7,883 a month, affordability is not a feature, it's a factor for building existing at all.
So the true value of Together at 45 is its ability to create resilience at multiple levels. For the community, it is more than just a disaster shelter. During extreme heat events, it becomes a safe refuge, providing thermal comfort, healthcare, support, clean water, and shaded spaces, along with its other activities. For our project partner, Aina, the shelter serves as a scalable model that they can replicate across heat-vulnerable, hot, arid regions. By combining traditional building methods with modern performance-driven design, it demonstrates how climate resilience can be achieved using local materials, community participation, and low-cost strategies. The project also creates measurable environmental value, achieving an 80.7% reduction in embodied carbon, a 50.8% reduction in energy demand, a 45% reduction in water consumption, and a thermal comfort for 99.3% of occupied hours that is further supported by the ambiator coolers. Ultimately, the project is not just about protecting people from the heat, it is improving their quality of life, strengthening their livelihoods, and giving vulnerable communities the resources they need to adapt in the rising temperatures. So we began this project with a question that stayed with us through every drawing and every simulation. What does architecture owe to someone who has nowhere to go when it is 45 degrees outside? Not a temporary shelter, not a crisis response that arrives after the damage has already been done. This building is our answer to that question, a place that cools before switched on, that gives back more water than it takes, that generates more energy than it consumes, and that is built from what the land already produces and is maintained by the people who built it. The numbers speak: 99.3% thermal comfort, 80% embodied carbon reduction, a net positive water cycle and energy balance. But the numbers are just a consequence, and the intention was always much simpler. A cool place to rest after hours in the sun, clean water during extreme heat, healthcare for someone who cannot afford to be sick, a space to learn, to skill, and to earn. And a community that does not have to scatter when the temperature rises because there is finally some place that they can come together. And that is what resilience looks like at 45 degrees. And through this project, our answer to whether architecture is ready to respond to rising temperatures of today's world is yes. Thank you.
Thank you, team. You finished well in time. Now let's hear jury comments. Mamta, you may go first.
Congratulations to all of you. A great presentation. I see a lot of groundwork with the AINA, your project partners, and the entire community over there. I would like to know that, let's say, if we have no electricity supply in extreme heat wave time, and outside temperatures are 44, that time how you have actually done this thermal comfort analysis, how much temperature difference we can see in that time. If you could just tell maybe most impactful three strategies which can be used for the project to achieve this temperature difference.
So like, first of all, we have done a simulation for 50 degrees Celsius. So it demonstrates 97% of thermal, it lies under 97% of working conditions and thermal comfort range. So that was one analysis which we had done. And for the energy backup, so like we have provided around 1000 kilowatt storage of battery, which it's useful for 3 days, which runs for 72 hours. So that is one.
So what are the three top impactful strategies?
Yeah, so assuming, like you told, when there is no electricity, if I have to pick the three passive strategies, one would be the Southern Walls rammed earth itself. So the thickness of it acts as a thermal buffer. So nights are very cool in Bhuj. So it retains the heat, and as it goes cooler, it also lets in heat, which works great with the temperature. Second would be the roof with the date palm board. We actually did a prototyping where we measured it for 7 days. We significant 3 to 4 degree drop we saw just in Bangalore temperatures as well. So that would be the second strategy that would help greatly in reducing the temperature and the height of the building itself. So we have the split roof system, which allows for hot air to escape, go up and escape. So it is almost double storied, and that would be the three strategies I would pick.
Good.
Well presented. And I think you've really worked well on your model. The couple of things. The form of the bunga is circular.
Yeah.
Moment you break that form, it's no longer circular.
Yeah.
Is right. It's no longer efficient for the reason it was made. Right. So you take the bunga, you made an oval, but you actually cut the oval also because it's separated.
Yeah.
For making your whatever design interventions. So fundamentally, it's not going to behave the way you imagine the bunga will behave. It will, because it also has its own right angles. I mean, at the cut. So that needs to be just to be aware. I'm making you aware. It's just yeah. Similarly, that also you're also operating in an extremely difficult area, just like the Andaman Nicobar earthquake as well as cyclones. Kutch also has cyclones, right? So the roof and its anchoring would become extremely important because especially the court would actually uplift your roof. So you would want to be careful about how you handle. It's not a court actually; it's more a passage. So the court would be actually closed on four sides and open to sky. So it's more like a veranda, a large veranda in the center of the building. In the context, so its behavior would be different from a court in that sense. Also, if you look at rammed earth, okay, bungas are adobe. They are not rammed earth, which means adobe is far more lesser dense compared to rammed earth. Rammed earth density is as good as brick, which means its absorption, I mean, thermal conductivity U values are more or less similar. So what you would get with brick, you would get with rammed earth. So whether you would want to think about these, because you had these columns, you had an idea which is very interesting, which is useful for your anchoring your roof also, which is that you have this, I mean, rammed earth kind of columns. You could have used the rest of the walls as adobe, maybe that could have helped you reduce, your heat gain during the day, because your walls are 2 floors. They're not protected by, they're continuously in radiation. So you would want to do something to that surface, not only radiation but also the rains. So obviously then you'd have to rethink the walls in a certain way. Adobe may not work beyond a point, or you have to redo this, and that's where the community can come in. Community can come in to repair these walls once in a year, and that kind of sets a system, because you're working with INA, which is very active in that part. The other important thing is water. You've looked at as even the groundwater.
No, we are recharging the groundwater.
But you actually calculated in your calculations. It looked like you calculated it for harvesting.
No, so we have underground water tanks. That main supply comes from rainwater and the municipality water. Rainwater is very less during only the rainfall season.
If you corrected it, it's all right. But earlier you had a calculation which seemed to show that you've actually taking that. So as long as you're aware, that's good.
Yes.
That's fair. So these were the larger comments, and the very important and very nice thing that you also added to your presentation was that you worked with the community and helped them retrofit the existing.
Yeah.
So other than your own personal project, you also looked around and you saw what simple solutions you could provide to something that also exists.
Yeah.
So these are the comments that I think I would like to share, and thank you.
I think for the Bunga derived form, we had to find the middle ground for the site that was existing as well. So that is what we did. And rammed earth we chose especially because that is Aina's specialty. They have been working when teaching the community there and building their homes and other places with rammed earth, and that was the choice that we made.
That idea was just to remember that you may be working with an agency, but you have your own minds.
Yeah.
Sir, about the structural part, which you were saying about the roof anchoring. So we have provided anchors to the roof itself, which is connected through steel sections, and it's connected with the beams and the load-bearing columns itself.
Yeah, I noted that. Yeah.
So, yeah.
Yeah. Good.
And again, in case of that roof covering which you had mentioned, so like it has this tile clips which protects it from the cyclones.
Yeah, you mentioned that.
Yeah.
Yeah. Good.
So, like the other jurors, I think the quality of work on ground with the community and the engagement, I think, is excellent. And I really appreciate all the effort you've taken, including working with IWST to develop these sections, prototyping. So, I think an excellent effort. One of my main complaints or weak points as far as the project is concerned is this inclusion of a cattle shelter. Okay. There's no reason apparent to me as to why you should have a cattle shelter. I don't think the community is such that they keep cattle. And bringing in a cattle shelter on your site adds to your problems because you have to also look at the water requirement of the cattle shelter. You have to look at cleanliness, hygiene, rules, regulations of the Bhuj Municipal Corporation in terms of having a cattle shelter. And then associated issues, including, what happens to the cattle shelter during a cyclonic event? What happens to the cattle shelter during a heat event? What happens to the cattle shelter during a seismic event? And to me, it seems like the cattle shelter is there and you're using it for biogas, but you haven't really engaged with the cattle shelter design, right? So why would you want to have a cattle shelter? It seems like only for the biogas potential. So if you could explain that, because for me, that's one weak point. Otherwise, I find that there are, of course, some interesting details that you've detailed out now, maybe after our last round of feedback, which I really appreciate. But for me, the cattle shelter part remains a weak point and a very sort of unclear point. So maybe you could elaborate a bit on that.
Yeah, so as we saw when we went there, not every family that did own cattle. They had smaller sheltered areas for the cubs to stay. But one thing that we were looking at is, would families hinder themselves from coming here if they have to leave the cattle near their houses or something like that? So it was a provision that we made, keeping in mind what they're actually right now doing in their daily lives as well. And that was why we...
So, at least unless I missed it, nowhere in the document have you mentioned about the cattle that this community keeps. And even in today's presentation, you haven't really talked much about the cattle shelter. So to me, it still remains a question as to whether it's really a cattle rearing community, and whether the cattle shelter was thought of because you wanted to ensure that there was a shelter for the cattle, as opposed to because it becomes a source of biogas and it helps you address your energy, sort of performance.
Yeah, it is not a cattle rearing community, but they do own, like I told, not every family, they do own cattle. And yeah, it was provided for the shelter as a whole that they could bring in during the peak heat months. So even for water calculations and all, we have considered as miscellaneous and under curve as well. So it is not completely left off, I would say, but yeah, maybe we could have detailed out.
I thought also interesting. I think you could improve your water performance by you actually calculated 24 hours and in the peak season also.
Yeah.
But you won't need the PDEC 24 hours. You would need it in peak heat. So it probably around 8 o'clock. This is desert. By 8, 9, 10 max. The evenings are cool. So PDEC the water may not be needed at that time in the PDEC system. So you may actually calculate 18 hours or 16 hours or 14 hours as per. So you would reduce your water usage and your calculations would change.
Okay. Yes, sir.
One last point, because you have already done a great work around existing stock, building stock, and the retrofit. So when you have done a lot of interaction before the project within a community over there, how have you positioned this green awareness or educational outreach in the operations? So whatever you are working on, at the project level, how do you ensure that operational, team or the, people over there are able to understand these features, appreciate these features, and run these features in the long term? So I am not expecting answers right now in respect to the time, but I'm just like sharing this so that like you have the bigger perspective for the longer terms of the implementation. Thank you so much for
Thank you.
everything.
Thank you so much.
Thank you, jury members. Thank you, Team Amara. Let's take 5 minutes and get ready for the next presentation. Okay. Hello, everyone. Our fourth presentation is from Team Samanvaya. They have worked on a community resilience, heat stress, and food shelter in Devangiri district, Karnataka. Team, you will have 20 minutes to present your work to the jury. At 15 minutes, I'll ring a bell like this. You won't have 21st minute, which means at 20 minutes, I'll stop you and ask to end your presentation. After that, we will have 10 minutes for Q&A session. Please keep your answers direct and to the point. Okay, team, the stage is yours. Good luck.
Imagine being asked to trust a building you have never used before on the worst day of your life. Because when disaster strikes, people don't just seek shelter, they seek familiarity, community, and trust. Good afternoon to everyone present here. We are Team Samanvaya, a multidisciplinary team of future architects, engineers, and management professionals from institutions across India. And what began as a question about trust ultimately changed the way we thought about resilience. The story begins here.
Increase in temperature is because of the loss of the heat sink. Heat sinks are your water bodies and the vegetation. In the last 5 decades, we lost 88% green cover and 79% of water body. That is the root cause for the city.
Water sources have depleted due to encroachment of lakes. Tree felling has led to reduction in the green cover in this city.
Cities across India are facing a growing reality. Rising temperatures, increasing urban floods, and vulnerable communities living in fragile encroached settlements. For many families, these crises are not rare disasters, they are recurring conditions. When heat waves intensify, homes become uninhabitable. When heavy rains arrive, streets transform into flood channels, and when displacement happens, communities are often left with nowhere to go. In these moments, the question is simple: where do people find safety, relief, and support? In Davangere, a city that connects several surrounding rural settlements, we began asking a different question. What if resilience infrastructure didn't appear only during emergencies? What if it existed every day supporting the community in normal times while remaining ready for moments of crisis? This question became the starting point of our project. To understand the role this building could play, we began by studying the site and its surrounding community. The project sits on a compact 0.6-acre site adjacent to municipal worker housing, a dense residential area where families contribute to the functioning of the city's social infrastructure. Through site visits and conversations with residents, several everyday needs became clear. Access to basic healthcare such as nearby pharmacy was limited. The community needed a more organized space for weekly markets, small-scale economic activity, and local gatherings. At the same time, discussions with local authorities revealed another important role the building could play. During periods of extreme heat, urban flooding, or temporary displacement, the structure could function as a refuge and support center. This dual understanding shaped the project. Rather than remaining idle until disaster strikes, the community resilience shelter is designed to support everyday community life while remaining ready to respond during moments of crisis.
Site context. Our project is located in Chikkabudiyal village, Davangere, Karnataka. It functions as a community center during normal days and transforms into a 24/7 disaster shelter during emergencies. The site has an area of 2,596 square meters and is located within a warm and humid climate zone. Economic context. The economy is driven by agriculture, textile trade, education, and small scale industries. The project serves nearby villagers and municipal workers on normal days, and while flood affected, heat affected communities, and encroachment evicted victims during disasters. A key opportunity was the replicability of the project, and the primary challenge was the limited site area. Climate analysis. Temperatures ranges from 20 to 35 degrees throughout the year. Monsoon months, the humidity rises above 80%, and the mean yearly rainfall is 500 to 1300 mm. Most importantly, the psychometric analysis showed that nearly 83% of comfort hours could be achieved through passive design strategies, which became the basis of our design. Site analysis. The site is accessed through a 5-meter main road. The boundaries facing the community and the road are noisier and less private, while the interior provides quieter zones due to neighboring agricultural lands.
Form development and site plan. Multiple massing options were explored before arriving at the final form. Through courtyard integration, massing refinements, the final scheme improved daylight, ventilation, and thermal comfort while supporting flood resilience through stilt construction. The final L-shaped form responds to the site's geometry with entry at the main in the main road, landscape pockets, and peripheral plantation creating a climatic buffer. Design decision matrix. The matrix maps our design journey from assumptions to performance-based outcomes. For example, larger openings initially seemed beneficial for ventilation, but simulation showed increased heat gain. This led to control cross ventilation with optimized openings towards south, bringing down glare to 9%. Community center. The experience begins with a courtyard centered around a tree inspired by the traditional village setting. To one side are the ramp, clinic, and play area, and the other accommodates the administration, support staff, services, and a large corridor that connects to the still zone where markets, workshops, and dining activities take place. The upper floors contain multipurpose halls, workshop spaces, and sit-out spaces which encourage interaction. The corridor along the west was intentional to act as a thermal buffer. During disaster, the still spaces become assembly zones while the clinic remains operational. The multipurpose halls and workshop spaces transform into dormitories using flexible furniture within 40 minutes. The sections and elevations illustrate the stilted flood resilient structure, passive design features through windows, shading, and materials. The interior renders showcase a calm and comforting environment. The exterior renders highlight the stilted form nestled within the landscape. Together, the building and the surrounding tree cover creates a sense of healing and hope for the community. The journey mapping illustrates a day in life of the building, comparing normal conditions to a disaster scenario. Engineering and operations. The project uses a framed structural system with recycled reinforcement bars, eco concrete, and hollow CSEB blocks with cork insulation, achieving a U value of 0.4. The window system uses a low E bifold glazing with air cavity and adjustable louvers. Howdy filler slabs reduce the embodied carbon while the roof truss supports the insulated clay tile roof. Light shelves improve daylight penetration and isolated footings support the stilted flood resilient structure. Operations. Rather than a binary transition from community center to disaster shelter, the building operates through a progressive levels of emergency activation, allowing many everyday functions to continue during minor and moderate events while gradually increasing shelter capacity as required. The operations framework outlines the process from emergency arrival, medical screening, to shelter management, resource allocation, and recovery.
This project is the result of collaboration between technical experts, consultants, project partners, and community stakeholders. Their input strengthened the project's performance across carbon reduction, resource efficiency, and disaster resilience. Beyond conventional sustainability measures, we introduced innovations that deliver measurable impacts. Adaptive furniture enables rapid conversion of community spaces into emergency accommodation without additional floor area. Recycled C&D waste is repurposed into gabion walls and permeable paving, reducing landfill burden while improving site drainage. Bicycle power generation promotes community engagement with renewable energy, while mud lime finishes support thermal comfort, indoor air quality, and user well-being. Our passive design strategies increased annual comfort hours from 11.8% to 82.8%, representing a 71% improvement over the baseline. Daylight levels remain within the useful range of 300 to 2000 lux, while annual sunlight exposure is limited to just 9%, keeping glare below recommended thresholds. Together, these strategies reduce solar heat gain by 28% and maintain comfort indoor conditions for most of the year without any air conditioning. These outcomes are achieved through cross-ventilation, shaded openings, high thermal mass materials, optimized daylighting, and landscape strategies that improve the surrounding microclimate. The building achieves ventilation rates of 2 to 2.3 cubic meters per second, exceeding minimum standards and ensuring healthy indoor environments. Comfort is maintained primarily through passive means, supported by user-controlled openings and low-energy ceiling fans during peak summer conditions.
Our demand-first energy strategy combines envelope optimization with passive and efficient design measures to reduce operational energy demand by 66.6% compared to the baseline, significantly outperforming the Super ECBC benchmark. This reduction is achieved through high-performance wall and roof assemblies, optimized shading, daylighting, and naturally ventilated spaces that eliminate the need for air conditioning, resulting in a gross EPI of 12.11 kilowatt hour per square meter per year. The remaining demand is offset through rooftop solar generation, which exceeds annual consumption by 76.7%, making the project net positive in operational energy. During grid outages, critical services remain operational through battery backup, providing over 2 days of energy autonomy.
For water performance, the project achieves a net zero water strategy through efficient fixtures, rainwater harvesting, and grey water reuse, reducing potable water demand by 57% from the BIS baseline of 70 LPCD to 30 LPCD. Following a reduce, reuse, and recharge approach, the annual water balance is met through alternative water sources, resulting in a net surplus of approximately 43 kiloliters per year. During disaster conditions, stored potable water, harvested rainwater, and treated grey water provide a resilient backup supply for all operations, ensuring continuity of essential water services even during disruptions to municipal supply. The net water cycle diagram illustrates how water is collected, treated, stored, and reused across the site. Dedicated storage and treatment systems ensure a reliable support while reducing dependency on municipal water. For landscaping, xeriscaping eliminates freshwater use entirely, meeting the irrigation demand completely through treated grey water. On-site wastewater treatment enables continuous recycling of water, supporting both everyday operations and emergency resilience. The project uses an integrated water management system where rainwater, stormwater, and grey water are filtered, treated, and reused. As per the site plan, rooftop runoff first passes through gutters and debris screens, then through a first flush diverter, followed by sedimentation and filtration before entering storage. This reduces the risk of filter overload due to high dust or biomass events. Multiple stages of filtration, sedimentation, and natural wetland treatment ensure water quality and enhance resilience during both normal and emergency conditions. For resilience, the building uses dual-stage spatial programming. Daily, the stilt area, workshop, and multipurpose hall host community activities. During disasters, they instantly pivot. The elevated stilt floor becomes a flood-safe assembly zone. The halls convert to emergency dorms and solar panels switch to backup power. Centralized washrooms, vertical circulation, and a clinic ensures full emergency readiness. Our framework divides operation into 3 phases. Pre-disaster handles daily activities and thermal comfort. The alert phase triggers flood or heat mitigation and resource backups. The active response plan uses understructure water flow to combat flooding, night purge cooling for heat stress. Post-disaster, adaptive use reallocates workshop spaces for relief distribution, the hall for dorms, and the stilt area for community assembly. Climate adaptation relies on resilient architectural detailing. For heat resilience, the envelope combines CACB walls, caulk insulation, and mud and lime plaster for thermal buffering, paired with vertical fins and low-E louvers. For water resilience, we integrated recycled C&D waste gabion walls to break flood velocity, and permeable pavers for groundwater recharge, and raised stilts to secure a dry assembly floor. Our resilience strategy is measured through outcomes rather than individual interventions. The shelter accommodates up to 300 occupants, maintains over 2 days of energy autonomy, achieves 82.8% annual comfort hours without air conditioning, reduces potable water demand by 57%, and remains operational during disruptions to grid power, municipal water supply, and extreme weather events. We feature a fire extinguisher layout and clear evacuation routes. Modular benches mechanically convert into emergency bunk beds during the time for disaster.
Coming to embodied carbon, we've achieved a major reduction from 768.6 to 225.4 emissions per functional unit, which is about 70.7% reduction. This was achieved through low carbon materials, optimized construction systems, and resource efficient design strategies across the building. Along with the reduction numbers, we also looked at how these systems perform over time through durability, maintenance, and local feasibility. So for the wall, conventional brick masonry was replaced with a low carbon CSEB wall system, reducing wall carbon by about 78.4%. To make this strategy locally grounded, around 731 tons of suitable soil is required for CSEB production. This equals about 490 meter cube of excavation, which can be achieved through an average 190 side cut across the total site. This wall buildup keeps smart plaster on protected internal surfaces while the exterior is protected using siloxane treatment for better durability. For flooring and site work, C&D waste permeable pavers and recycled aggregates are used to reduce emissions while also improving stormwater percolation. In the structural system, filler slabs helped reduce concrete volume and dead load. For the roof, clay tiles and caulk insulation reduced both heat gain and embodied carbon. For openings, timber-based frames helped reduce aluminium dependency. Together, these systems make the building lower carbon while still remaining practical, buildable, and maintainable through simple inspection and replacement cycles. Coming to affordability, the proposed project cost is 76.15 million, which is 20.5% lower than the baseline. The cost estimate is based on Karnataka's schedule of rates, project-specific assumptions, and also the market references. The annual OPEX is 1.55 million, which is only about 2.04% of CAPEX. The project also achieves a 25-year life cycle cost of 90.76 million, giving a 25.1% from the baseline. The LCC was calculated as an initial capital cost plus the discounted operation and maintenance cost and also the discounted replacement cost. So in our case, this is approximately 76.10 million plus 14.07 million plus 0.59 million, which gives us 90.76 million of LCC. The reduction comes from lower initial cost, passive design reducing operational demand, and durable systems with manageable maintenance cycles. The facility is not only planned as a disaster shelter, but also a 365-day community asset. It supports meetings, workshops, and medical health facilities with projected revenue of 5.6 lakhs per year, offsetting nearly 36% of the OPEX, 36% of the annual OPEX. The project creates value for multiple stakeholders. For staff and karamcharis, it provides rest areas, toilets, drinking water and cleaning support. For the disaster affected users, it provides shelter for 300 occupants while sleeping, sanitation, water and medical health support. For the Davangere City Corporation, it becomes a lower cost, daily use and emergency ready public asset. So the built up area is used effectively through multi-use programming. These spaces serve as a community area during the regular days and as a disaster shelter during the disasters. So overall, the project combines measurable benefits with social value. It improves thermal comfort, reduces water and emergency dependency, supports livelihood activities and strengthens emergency preparedness. So the proposal is not only sustainable on paper, but also usable, affordable and resilient for the community in everyday life and during the disasters.
To validate our wall assembly, we developed a physical component model using CSCB hollow interlocking blocks, cork insulation and stabilized mudlime plaster. Prior to this presentation, a conventional brick sample and our proposed wall sample were exposed to the same heat source under identical conditions. The temperatures were recorded from both samples. The proposed sample shows an internal temperature approximately 2 to 3 degrees Celsius lower than the conventional brick sample, demonstrating the thermal benefit of the insulation and earthen materials used in our wall system. To conclude, our proposal demonstrates how a community center can function as both everyday community infrastructure and climate resilient disaster infrastructure. The project achieves a net positive energy performance, a 57% reduction in potable water demand, a 70.7% reduction in embodied carbon, a 20.1% reduction in total capital cost, and significantly improved occupant comfort. So, what if the strongest disaster infrastructure is a building that you already trust? Thank you. Thank you, team. You did a great job. Let's hear jury's comments and take questions from them.
Okay, so to begin with, a lot of interesting work in terms of right from the first question you ask and the question you end with. So I think that's extremely important. And my question, in a way, is with respect to this question itself. What is the use case? So normally a use case will be based on the fact that this community that you're targeting already has faced evacuation scenarios or is likely to face evacuation scenarios given the kind of changes we are seeing with climate change, etc. And second is that while you're designing a community shelter and a community building, what is the use case during regular times and the business case for it? So, and my concern, so while I really like the approach and I really like the work you've done, my concern is that have you ended up designing something which has a larger building footprint than which can run successfully in terms of, because running a building like that and keeping it operational also requires a lot of effort, investment, programming, personnel, and communities themselves are not necessarily in a position to run a center like that. So I think that there is some gap or there is something there which I'm not able to get a sense of from your report or even from your presentation.
So I think this is the white elephant part you were talking about, sir. So this project wouldn't become a white elephant because we've actually noticed that there are lack of medical support, and they even for taking vegetables they have to go to the city, the main Davangere city, which is about 16 kilometers from the construction from the Karamcharis where they stay, the community. So this would be very busy during all the other regular days, and it wouldn't become a white elephant is what we are proposing, because it is closer to the farms which are cultivating vegetables, so then they can come and sell their vegetables in the space. And then it is they also do not have function spaces for birthdays and for some other thing, and they can use these multi-purpose halls for that, and the revenue is generated for the building. So it wouldn't become a white elephant is what we are proposing.
Congratulations for getting into finals. I wish you all have good learnings and best of luck for all your future endeavors. I saw a good slide in your presentation wherein you were showing a normal day look likes and a disaster day looks like, right? And I also see, a couple of slides where when you were, that's okay, don't jump onto that. Uh, and I also see in a couple of slides wherein you were emphasizing how your collaborative innovation has come into place to increase the performance of the building. I am yet to, like come on a conclusion. Let's say on a disaster day, plan A, plan B, plan C. If you could just run me through that, let's say what a disaster day plan A looks like. What if the plan A fails? What a plan B looks like? What if the plan B fails? Did you understand the question?
So the plan is on a normal day it functions as a community center. So they it on a plan on a normal day it functions as a community center as a market space, etc. But on a disaster day, first since our particular site doesn't lie in the disaster risk space, so since the water flows towards the river, our site doesn't accumulate any water, so it is a little safer. It is a safe space for where they are guided to, and if it's flood or heat, they are then notified from the villagers where they are affected, and they're guided to the community center. And once they're brought up, first they're assembled in the assembly zone, that is the stilt areas, and then they're taken, if any medical help is required, that is taken care of immediately. And then they are taken to the dormitories where these the sofas that we have proposed for normal days convert into a bed double decker bed where they're all accommodated, and likewise the operations, water, energy that they've talked about continues.
Can
So
you
if
emphasize a little on energy, water? Let's say a flood comes and you have how many people you are planned for? 200, 500? 300. Let's say 300 people are there inside. And now no electricity, no water coming in, maybe, let's assume.
So in that, considering the scenario that it's a case of disaster, and with regards to water and solar, we have water autonomy, because our site is most of the time in surplus as per the water consumption table and all the calculations. And for solar also, we have 2 days of power backup in case of complete electricity cutout. So like that is the initial stages of preparedness we have for water and solar.
Okay, we can have a little more discussion after, after the session, maybe onto this. Thank you.
Yeah, hi. Really well presented case as a presentation in terms of being able to go through page 1, 2, 3, 4, 5. One of the challenges of this competition is for many of us as jurors is that, and I think you've done a very good job in that aspect in terms of going through very clearly, very pragmatic, I would say. Just like your design, which is also very pragmatic, which is what one of the things that I would like to appreciate, that it's a kind of a project which you could actually, with the available materials right now, you may not have been extremely innovative, but you've been pragmatically innovative of using existing materials and systems. For example, jalis, louvers, the way you've actually talked about your block, and you've actually very nicely shown us how you're actually going to manufacture it, putting it together, the insulation, which is quite a practical way of, and I think sensible also. So in many ways, and using debris, I also like the idea of the design, which basically opens up the ground, because in disasters, there's a sense of immediacy, and the ground which is available, as you said, for markets and other things on a daily basis, and otherwise immediate access for shelter, and even for heat, one could just walk in and settle. I like the idea of the ramp that goes up, which is easy to go. I would have suggested that the ramp goes to the terrace, and the terrace is basically filled up with earth, so you could actually get better EPI, because right now you could actually improve your EPI if your roof also had earth on it, which is possible given the way the project is located, project is handled. The important thing, I think, you could have there is this light shelf that you've used, and I think something about it that you could improve. I remember that during my evaluation, and I mentioned that on the second floor or somewhere it is.
Yes. So, sir, what we did was, what the mistake you mentioned in the comments was that our first and second floor light shelves were, were placed here, which was a mistake, and you asked us to change it to how it is in the first floor. So we
Okay.
rectified that.
Good. Good. So overall, I think personally, I found it extremely pragmatic as a project, and it's interesting to see how you presented it, and all these cycles, whether it's water, whether it is air. So you've ticked the boxes pretty well in simple ways. So congratulations and good luck.
Also, I would like to add, so our project partner is the Davangere City Corporation, which is a government body taking care of the city there. So while being in touch throughout the project, we made sure that all their concerns were addressed. And their ask from the start was to keep it very economical, very simple, yet a very good building that they could replicate and scale it across. So, which is why we have come to solutions which can be replicated easily and also are easy to make for the locals as well. Thank you, Team Samanvaya. We will now take a long break for lunch, and we will be back for the presentation at 2:30 p.m. And Team Genius Loci would be presenting at sharp 2:30. And folks online, I request you to stay tuned and join us for the upcoming presentations. Thank you.
is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through.
Hello, good afternoon, everyone. Hope you enjoyed your lunch. So, welcome back. Welcome to the Community Resilience Shelter Division. Our fifth presentation is from Team Genius Lukai. They have worked on a disaster resilient community shelter along the Spiti River near Kunzum Pass. Team, you will have 20 minutes to present your work to the jury. At 15 minutes, I'll signal like this. You won't have 21st minute, which means at 20 minutes I'll stop you and ask to end your presentation. After that, we will have 10 minutes for Q&A session. Please keep your answers direct and to the point. Okay, the stage is yours. Good luck.
Good afternoon, everyone. We are Team Genius Loci, a multidisciplinary team with architects, engineers, PhD scholars, along with faculty mentors from IIT Kharagpur. We are working alongside the World Bank and the HPSDMA on this community resilience shelter. This is Losser. Sitting at an altitude of nearly 4,000 meters above sea level, it is a remote, beautiful, and an extreme landscape. Losser lies in a highly vulnerable seismic zone and is also exposed to multiple hazards, including flash floods, landslides, avalanche, and GLOF. Our initial studies revealed something interesting. So the very conditions that make Losser vulnerable are also its greatest resources. Sub-zero temperatures, high solar radiation, and a unique precipitation pattern are not just challenges, but they are just opportunities waiting to be harnessed. However, while literature and research helped us understand the physical fabric of Losser, what it failed to make us understand was the community life itself. So to understand the community better, we had partnered with our industry partner, which is Muse Initiatives. So they are an NGO who are active in the Spiti region. They work locally with the village people, the village community, not limited to Losser, but like they've worked with multiple villages in the Spiti region. So we had partnered with them, and also for our data collection regarding the Losser community, with the help of a institute IIT Kharagpur, we found contacts from the community, the village itself, to gain more insight on the community life. So a couple of meetings with all these stakeholders revealed that Losser is not static. So we carefully mapped out the village's life across all seasons. So we found out that the entire fabric is dynamic and the community changes with its with the dynamic itself. So the project brief was simple. Design a community resilience shelter for tourists and locals, but our conversations with the community revealed a much deeper reality. My uncle had to carry a tourist for 6 kilometers to seek medical help during a road blockage. A family had to accommodate a neighboring village's family during a flash flood incident for about a month. So these were direct testimonials from the community itself. So the challenge, therefore, was not just to create a shelter, but build a foundation that allows Losser to remain self-sustaining in everyday life and resilient during emergencies. So our proposition was simple. Nothing is wasted, nothing is redundant, every space earns its footprint twice. One building, zero dark days. So in the following slides, we will take you through our design process and not just the numbers and the achieved percentage reduction values, so that you can understand why we did what we did. So our design process started with a very fundamental question. How many lives does this building cater to? So because this was not designed as a single purpose building. So Losser residents, stranded tourists and displaced villages. So we mapped their activity, we mapped their activity inside the village throughout the year. So for Lhasa residents, this building is going to work as a year-round community center. But for standard tourists and displaced villages, it's going to be seasonal and it's unpredictable as well. So during this activity, we found that the peak demand, the overlap window was between July and August. So that came down to 85 to 105 people that the building should cater to, like during a disaster situation. So combining that with the sphere standards, about 4.5 to 5.5 meters square per person, we arrived at our built-up area. Why this was crucial is because the site area that was given to us was not that much. It was hardly 420 square meters. So whatever space that we were building was going to should cater to the peak occupancy. Next. So after finding the occupancy peak occupancy demand of the building, we jotted down the use case scenarios of the building. So there's going to be tourism and community interaction in June and October. Scenario 2 is going to be winter community life, where there are not going to be tourists because of the road blockage. And scenario 3 is going to be a disaster relief shelter itself. So during that scenario is when the standard tourists and the neighboring village people are also going to be the users. So, no, previous slide. So after we jotted down these use case scenarios, one thing was simple. So we had to come up with a flexible spatial layout. So since it's going to be a single building, we divided the spatial needs into two components. One is fixed, another is flexible. So the fixed modules are basically the service or the supporting spaces, which include circulation, service, and a social space also. But since I also mentioned site constraint and built-up area constraint, we had to combine the circulation and the social space, and we created a single flight staircase, which is going to act as a social spine. So it runs from ground floor to second floor throughout the building with 2-meter width and like deeper landings. That staircase itself can act as a community gathering space as well. Next. So we combined our spatial needs with the thermal zoning. So we had to come up with a layout for that. So can you? So like I said, on the northern and the eastern part, we fixed our 1 and 4 modules, which is the service spaces, toilets, and the circulation, the spine, the staircase. That's going to act like a thermal buffer. So as you can see, the northeast and the west, north and the eastern side are completely fixed. And what the southern, the 3 part, right? The middle part. So that is the southwestern part, which was based on the simulations. We found out that that's the most thermally comfortable zone. So we had to zone our flexible and adaptive spaces in that area. So these are the different scenario use cases of the building. So all these activities and in detail about how the planning itself is going to be adaptive is going to be covered in the following contests. So how does the building or the envelope or the form of the building is going to cater to the inside spatial layout? So we combined architectural and cultural identity. That was something that we had to preserve as well, since it's going to be a community based, and the functional and the energy efficient aspects of it is going to be covered in the following slides.
So at Lhasa, the question was not how to design a building. The question was how to keep a building operational when temperatures are low, freezing, roads are closed for months, and emergency response can take days at a time, and simple enough for a community to build and maintain. So our engineering strategy, therefore, focused on resilience through simplicity. Our project partner emphasized that the building should be easy to construct, repair, and operate locally. Therefore, we adopted a hybrid construction system that separates structural performance from thermal performance. The site lies in a high seismic risk Himalayan region, so all the gravity and lateral loads are carried by a ductile RCC moment resisting frame designed according to the IS codes. Instead of heavy masonry, we used straw clay walls as non-structural infill, reducing seismic mass while improving thermal comfort. So, inspired by the successful Himalayan precedents such as Hial case studies, this approach allowed us to work with a construction language familiar to the local communities. And a mineral wool separation joint between the frame and the wall accommodates the seismic and thermal movement while preventing cracking. To address the durability in extreme cold, the structure is protected through adequate concrete cover, breathable lime finishes, controlled drainage, roof overhangs, and raised stone plinth. Our strategy is simple: to keep this assembly dry and freeze thaw risks are minimized. So the building operationally integrates 47.2 kilowatt per solar microgrid, water harvesting, wastewater reuse, decentralized wastewater management into a single low maintenance system. All the systems are right sized according to the occupancy load, and this results a community manageable shelter that combines engineered seismic safety, passive thermal performance, and operational continuity.
Coming to collaborative innovation, so our intent was not just to design a shelter that is sitting there, but to create one that is resilient to both physical context and also serving the community. So we collaborated with multiple entities throughout our project at different stages, and they influenced our design decisions. The first being our industry partner Muse. They are a local NGOs doing very good work within the community itself. They have developed solar rooms and provided solar panels and done other social work as well within Loser and surrounding villages in the Spiti Valley. So they helped us connect with the local community. They helped us with surveys and they have given us a lot of insight into our design. Next is our project partners World Bank and HPS DMA. So they helped us establish our emergency protocol and they helped us understand resilience beyond just the physical infrastructure, and they helped us understand our financial aspects better. We also collaborated with the LOSA community itself. We had interviews with the locals, and like I said, Muse had helped us connect with them, and the stories that Maha had earlier stated, we got to know a lot about their perspective, the locals' perspective, through direct interaction with them. Lastly, we also are a multidisciplinary team, like she had mentioned. We have environmental engineers, structural engineers, and humanities scholars working with us. So that helped us look at the project, different facets of the project, and from multiple perspectives. So our collaboration resulted in these three primary innovations. So the first being these adaptive partition walls that we have fashioned with local materials, and these help in the dual function of the shelter during disaster as well as non-disaster periods. They help in the flexible spaces that were earlier shown. And the second one is the convertible beds. This flexible furniture also is one example of how the shelter is dual functional and can act as different spaces during different depending on the needs. And the third is the snow melt solar PV, wherein we have attached nichrome wires to the solar panels on the roof that we have provided, which heat up when there's a snow detected on the panels itself, and that results in melting of snow, which is then harvested and is part of our water management system, and it also results in better efficiency of the solar panels on the roof.
The first question we asked ourselves was, how do we make people comfortable at a minus 20 degrees Celsius in an emergency shelter? So first, we started with the base case. In the base case, we have seen that most of the people are uncomfortable in most of the period of the year. So our first aim was to start with the passive solar gain. So we introduced passive strategies like Trombe wall systems on the southern facade and greenhouse buffers, and also optimizing the window wall ratio on the south and west facades to have more solar gain into the building. But this has improved a lot in our winter temperatures, but has another problem to it, that is the summer overheating. So because of that, we have introduced micro louvers, shading system, and also we have made the glass configuration more better so that we don't have the summer overheating. We have reduced the temperatures to the comfort levels even in summers, and due to this we have achieved 80% comfort hours with only passive strategies. This helped us in achieving that we could have comfort hours without even during the power outages or even during the emergency when we have no connection with the outdoor service facilities. And we, through our stakeholders, we found out that the tourists and the locals have different comfort levels. So tourists are comfortable at a higher temperatures, whereas locals, they are adapted to the lower temperatures. So for that, we have introduced target infrared heating system. So this only in the main regions, not in the entire building, so that it will reduce our energy demand also, and also help in achieving more comfort levels for all the users. And then next. Then uh, for comfort, we haven't not only looked at thermal because people are stuck indoors for days and weeks. So daylighting is very important for us as it is also a psychological well-being factor for it. So when we have done the simulations, we have understood that we have very optimum daylighting within the building. But another problem we faced was the glare. We had about 30% glare in the building. So, but after adding the shading device and the micro louvers, that has reduced to 16%, and that has helped in creating better indoor daylighting areas. And then in the ventilation and indoor air quality, we have used the different seasonal ventilation strategies. In summers, we have used like windows remain open and we have mainly dependent on cross ventilation. Whereas through winters, we are dependent on stack ventilation and the central social spine staircase that acts as a vertical shaft which helps in ventilation throughout the building due to controlled window openings in the winter season. Next. Energy, we have introduced different passive strategies and to reduce the energy to about 66.5%, and our final EPI came down to 20.63%. And for resilience part, we have introduced the solar grid system, smart grid system. With this, during the isolation period, we get power from our solar panels. If we don't have any power, we have another backup system, that is the Himalayan rocket stuff that could be used as heaters for the building. It doesn't require any electricity. It could also be used for cooking purposes. Next.
Coming to water performance, as you can see, we devised different water consumption patterns during disaster and non-disaster scenarios, and this is a breakdown of how much quantity of water is being sourced from different water sources. To accommodate different uses throughout the year and different seasons and the water availability during all seasons, we have multiple sources of water, that is borewell extraction from the ground itself, harvested snow melt during winters, like I earlier said, the solar panels with the nichrome wires helps with that, harvested rainwater in the monsoon season, and recycled wastewater as well. Next. So this is the wastewater treatment system that we are providing, and all the pipes that are exposed to the external climate are insulated, and all equipment of the wastewater treatment system and supply system as well are placed below the frost line, which is around 2 meters below the ground level, to ensure that there's no freezing and frost formation during winters where it reaches sub-zero temperatures. And these are the different measures we've taken for frost protection and for earthquake resistance, and to ensure there's no freezing. There's no overhead tank on top of the roof, but there's direct supply from the pipe from the supply system to the taps within the building.
So the embodied carbon, like most of our reduction came from the walls. So the walls are carbon negative, and we can see a reduction from 700 kilos to 200 kilos. It is like 510.2 kilograms. So we used construction techniques like on-site earth utilization, lightweight systems, so that all the straw clay blocks are made on site, and we reduce the transport. So most commonly, resilient shelters are designed for a day that disaster happens, but our challenge is different. We want it to be valuable throughout the year. So these are all we have seen in the other slides covered. So our main focus was on the social and community resilience. Most shelters remain unused for most of the life. Tanza functions as a daily community hub, artisan workspace, and training center. We have integrated many schemes, vibrant village programs, broader area development program, through which the community center stays funded and it can operate on itself. Economically, it is stable.
Coming to affordability, we have taken multiple strategies to reduce the overall cost or capex and opex of the project itself. First is the usage of materials, the straw clay wall and the limestone flooring, which is sourced locally. Then there's the reduced HVAC usage because of passive strategies that we've used in the design. And also lighting load is reduced because of the natural daylighting that is provided in the southern side and on the western side as well. And the construction techniques themselves are simplified so that labor wouldn't have to be imported, and it can be done with the skills of the local community itself.
So we made sure that this building is gonna be like an enabler for the community. So with this building and its year on operability and all these number values or achievements, we can approach. Can you go to the next slide? It's like a pathway. It's a gateway to fund the building through government schemes. We made our best to standardize these procedures and not just community participation and community feedback to make it more practical and feasible. We had institutional partnerships. So for example, one example for that is the straw clay wall material, right? So they use that in Lhasa village. They make their own blocks, the straw clay blocks. So these are visuals from the village. So to strengthen the feasibility and practicality of this, we had imported the straw and clay that they use over there. And we made the component model with the help of IISc CST, the Center of Sustainable Technology. Thank you.
Thank you, team. You delivered it really well. Now let's hear from the jury.
Lunch के बाद we all push each other कि आप पहले. Good work. I think the important thing in this case has been the fundamental operative aspect of double wall, which is basically a good aspect in, I would say, in most climates, but especially in this extremely extreme climate. So the double wall kind of, and in that double wall, you've interestingly put your staircase and you put your other services. So as a design move, I think that's a very interesting and a simple move. I'm wondering whether the detail of the Trombe wall you have not mentioned. You just assume that everybody knows the Trombe wall, but I think it's important to understand that the Trombe wall captures heat in the day, but also gives you cold in the night. So how do you manage that? Do you know?
So we have introduced vents in the Trombe wall system in the above and the bottoms. So we close the vents during the night so that we don't have heat loss from the building. And during the day, we have a glass facade on the outer side of the Trombe wall. So that takes up the takes up more radiation and heats the air in the air gap itself. That helps in and the vents help in air circulation into the building.
Yeah, that was one. Then, what did you think about dry toilets in these parts? Because what happens is it's very low humidity, and one of the problems of these places is how do you get rid of waste? And did you think of a system that other than the normal system you could have used? There are other systems.
Yes, we had actually considered dry toilets as an alternative to regular toilets, and we had noted that point in our feedback as well. But we had decided against it during our around D1, D2 stage itself, because first of all, there is usage of dry toilets within the village in individual residences. But this being a public building with such high footfall during tourism season and even during disaster season, there might be very high occupancy if tourists are stuck there. Even there was a landslide today near Shimla, in fact, where then tourists were blocked within that area. So in such a case, in such high footfall, maintenance, very high maintenance would be required for dry toilets, and in such cases, tourists not being accustomed to it, and the maintenance and hygiene issues would be.
But in a disaster, your water would be an issue, and so you would have other issues. So I think it's a balanced thing. You'd have to figure out a way, because if the village is already using that, and one must probe that why they have not yet left that system. So it's something that you must research a bit more on that.
Yes.
We can discuss that later, but fundamentally, that if you're saying that the village uses, then I'm more convinced that we should think about it more seriously.
The
Yeah.
village does use it. Sorry. We did speak to our industry partner about it as well, one of the local contractors working there on behalf of Muse. And he did mention that within residences, the older ones it is used, but most tourist homestays and such, they do provide water supply and
That's for
flushing.
tourists, because the tourists will use. But in disaster, you're talking about the local community, right? Disaster mostly. Mostly in disasters, it's the local community that will use this place. Is the assumption that few tourists may be stuck here, but largely locals, right? Is an assumption I'm assuming.
Serving both user groups equally is the assumption under which we design.
Yeah, I think we'll leave that there. The idea of elevators and RCC in extreme climates is also an issue, because RCC doesn't behave well in extreme climates. So why did you go for, first of all, even 2 floors? You could have used, most of your stuff could have finished in 1 floor if possible. Then you wouldn't need RCC. Maybe even for this height. I don't think in 2-floor structures in those parts, they still use RCC. They don't. So why did you use RCC? And obviously then did you think about the elevator problem?
Okay. So, as I have already mentioned, our design documentation started with the occupancy because we were given a brief to accommodate at least 100 people during disasters. So, when we backworked it to see if the Losser community needs that amount of amount of area, we came to a conclusion that since it's going to be a disaster space as well, if we have deliberately left space on the ground floor in the entry area so that because it's like on the ground floor, it's the entry area and it will act like a triage and everything. So we had carefully spaced every space. The area that was the sphere standards was used for every space. So when we did all of that by book, and we came to a conclusion that we needed one more floor to accommodate the peak occupancy that was there. We were like, what good of a building would it be if it is not gonna house all the standard tourists or like the targeted people?
RCC?
And also, yeah, RCC. So the Muse initiatives, right, our industry partners. So they were telling us that local villages who are using RCC, straw clay construction, they are not everyone is like equipped with it, and like the project construction timeline and everything, they suggested that a hybrid system of a RC frame structure like in a seismic zone and a infill wall construction is going to be more efficient. And also to cite the Hayal's Institute, which is led by Mr. Sonam Wangchuk. So they are also in the process of standardizing the structure because the vernacular materials do not have like IS codes or any standards. So in an attempt to standardize the construction itself, we are using a hybrid construction system.
Yeah, I think this is the other thing that somehow the market, I think this is just off the record kind of thing, for this thing, but a lot of times the market pushes you towards certain elements.
Okay.
So you have to be, as a designer, be smart and see, okay, if RCC is going to suffer, can you use it in the second wall? And can the outside wall be, the other wall that can take all these temperature changes?
Okay.
So the RCC then becomes, so the design then can play a role in we understand what is the reality, but then as designers, we can take a call.
Okay.
How do we smartly integrate the two? Yeah?
Okay.
Well, all the best.
Thank you.
Good presentation.
Thank you.
Congratulations again for making it to finals.
Thank you.
A couple of slides, was mentioning about, why you are implementing certain strategies, and, you had nicely quantified its impact. One of, you also mentioned that the narrative which you got from, the team members over there was not to just focus on the design, but more focus around the operational continuity of the, the building. How do you make it simple and, the repair and retrofits local over there? So while you were doing these, interactions or study over there, what 3 challenges you find over there, which is difficult to operate, and which you solved into your project?
Okay, one of it just straight on top of my mind is the service disruption, like the electricity and water services disruption. And we do not have municipal water supply there. And in times of disasters, the electricity grid, like it completely goes off the grid. So I think we have solved that one major issue. And in terms of standard tourists, in disaster times for the local, apart from the locals, there are other stakeholders as well. So before this proposal or before this infrastructure, there was no infrastructure that could support a multiple range of stakeholders. So like Losser was carrying a burden that it was not ready to carry. So this building, since it's the thermal comfort ranges, we have equipped for a multiple, like a range of stakeholders. I feel like this building can accommodate a dynamic situation like that. So with our
Yeah, go ahead.
okay, so that I think is the second strategy that we did, and third one is there was a lack of economic like there was a lack of infrastructure where the village community people could generate their income. So they were focused mainly on agriculture, subsistence farming and everything. So during winter community, like the winter life where the agriculture is not really blooming, so they just sit in their houses seeking comfort, like going into the kitchen, lighting a fire, seeking thermal comfort and everything. So this, our building, like I said, can be like an enabler. So like we are providing an opportunity for them to use it. They can become a self-sustaining community because of this. And also, since that it is an active tourist space as well, the tourists can also like engage with the community. The skill studio, skill training workshops can be done, so their local crafts and everything can be known to the tourists. It's like a reach, like for the community.
Okay, my question was more from the operation and maintenance perspective. So how
Okay.
do you, repair or retrofit and the solutions over there? Because you might be using certain technologies or some, design parameters,
Okay.
which might be difficult for them, to repair in the operations, maybe down the line 2 years, 3 years, 5 years, or maybe 10, 20 years. If you could highlight something like that. You mentioned number one is electricity continuity or water continuity. Yeah, so that maybe something from that can come.
And another issue was the thermal comfort. Like there, most of the buildings now they are mostly made of AAC blocks, which does not have like they can't withstand those negative temperatures, sub-zero temperatures of that area. So that was one of the challenges, and also they also lead to summer overheating also. So that we have solved it in our building.
Like a simple operative protocol wherein to prevent the overheating, we just have the micro lower system, right? So whatever strategy we used for maximum solar gain is going to be a disadvantage during summers. So through a simple covering of the windows, like by 50% of the windows, and the Trombe wall system as well, like the vents being closed and open, these are simple strategies, like protocols that the users can do to have thermal comfort throughout the year, like both in summer and winters.
Very nice. Thank you.
So one is, I think, congratulations for taking on a problem which is very complex, which is in extreme condition, and there probably aren't many case studies or examples to go by. So I think great effort. There were a couple of observations that I thought, and I don't necessarily need you to respond, but maybe just leave you with. So we had a discussion on the toilets and the use of water. So even if you stay with the conventional toilet system, your design currently is showing a 10% reduction from base case scenario. So I don't know whether there was a way, while using a water-based system, to bring down the usage further. And maybe to think that in case we run out of water, do we have a backup system which is a dry toilet system that people can use? Because it's that scenario can arrive. So that was one thing. And this area has a lot of sheep wool, and as you probably know, sheep wool is not finding a market. So instead of using mineral wool, to think of some sheep wool based insulation material, rugs, more use of sheep wool would also link it back to the community and the kind of socio-economic, ecological scenario on ground.
So, do you want to take a sheep?
So we have run simulations based on different materials we use, like which would be ideal for the conditions, which will give a better indoor temperatures. So we have run simulations for sheep wool, mineral wool. So we found that mineral wool was better. That was one reason for it, and also was the standard procedures or the standard construction codes available for the materials. That was also one thing. Since we were going for those schemes she has shown before, so we need to have a standard materials and construction techniques to have the schemes allotted to us. So that was also one reason which sheepwool was not available for. So that was also another reason we didn't take it.
Thank you, jury members. Thank you, Team Genius Lukai. Let's take 5 minutes and get ready for the next presentation. They have worked on a resilient infrastructure social empowerment in Delhi. Team, you will have 20 minutes to present your work. At 15 minutes, I'll ring a signal like this. You won't have a 21st minute, which means at 20 minutes, I'll stop you and ask to end your presentation. After that, we'll have a 10 minutes Q&A session. Please keep your answers direct and to the point. Okay, team, the stage is yours. Good luck.
Good afternoon, respected jury members. Solace. The word solace means comfort, refuge, and reassurance. As a team, we believe architecture should do more than provide shelter. It should provide dignity, opportunity, and resilience. We are Team Solace from Jamia Millia Islamia. Our team brings together 12 members working across design, research, and execution. For us, resilient architecture must serve communities socially, economically, and environmentally, not just physically. Our journey began by understanding two vulnerable communities living in the Yamuna Khadar belt in Delhi. The first community consists of rag pickers. Despite playing an important role in the recycling ecosystem, many face economic insecurity, social exclusion, and limited access to opportunities. This is the community that was displaced by the 23 Yamuna floods. Coming to the second community, the present day community beside the Yamuna belt, this group consists of farmers living along the floodplains. Every year, these families face the threat of seasonal flooding. Both our communities share a common challenge, vulnerability. One struggles with economic instability while the other faces recurring environmental disasters. To understand their realities more deeply, we partnered with Manav Vikas Foundation, an NGO that has been actively working in the Yamuna Khadar region through food and cloth distribution, education, and free legal aid. Most disaster shelters remain inactive for the majority of the year and become relevant only during emergencies. At the same time, community centers often fail to address long term resilience and livelihood generation. This led us to a fundamental question: what if resilience was not just during the crisis but everyday life? This question became the foundation of our project. The site is located at Trilokpuri in East Delhi and falls within the composite climatic zone, characterized by hot summers, monsoon rainfall, and significant seasonal variations. The site is approximately 1980 square meters with a permissible FAR of 1.2. Our proposal utilizes 1635 square meters of built up area, achieving efficient ground coverage. To develop a meaningful response, our team adopted a structured 9 stage process. We began by engaging directly with families of the communities and our project partner, analyzing their social, economic, and environmental challenges, and defining the resilience not only as a protection from disasters but also as the ability to sustain livelihoods. The outcome of this process is RISE, Resilient Infrastructure for Social Empowerment. RISE is a dual mode community resilient shelter. During normal days, it functions as livelihood and community development center, providing spaces for skill development, recycling workshops, healthcare, learning, and community interaction. During disaster situation, the same building transforms into the emergency shelter. It is a framework that transforms vulnerability into opportunity. And with this vision established, Rida will continue forward from here.
There is a famous quote that goes, "When you know your why, you can find your way." And to define this why, we studied the resilience framework given by the United Nations Office for Disaster Risk Reduction, NIST, and Rockefeller Foundation. While each framework approached resilience differently, they all pointed towards a common understanding. Solution to present and future floods, solution to the past impact of flood, that is our displaced community A, and adapting to the needs of both the communities. A resilient community must be socially connected, economically empowered, and environmentally responsive. This understanding became the foundation of RISE. With our on-ground survey, understanding the community condition, we present onwards. Starting with the economic dimension, we identified a critical challenge shared by both the communities. The rag pickers community possessed the knowledge of the waste streams, but they had limited opportunities to generate a high-value income. Similarly, women and youth lacked in access to skill development and entrepreneurship opportunities. At the same time, a large quantities of recyclable materials leaves us with no meaningful value. This was the base of our economic philosophy. Instead of viewing waste as a burden, we transformed it into a resource. We introduced a high-value recycling workshop, a community market, and a community kitchen and a tailoring workshop. Together, these spaces create an ecosystem where learning, production, entrepreneurship, and social interaction all occurs simultaneously. These workshops become the economic engine of our project. Collected paper waste is converted into paper bricks and handcrafted lamps. Plastic waste is transformed into usable filament products, which is used for 3D printing. Every room is a mechanism for economic resilience, defining all our spaces in the building rise. With the following profit, these are the following profits of per person per member, and these are our feasibility analysis of the working business module. Having addressed the livelihood, we then focus on the social resilience. We observed that opportunities for informal interactions were limited. Many spaces felt restricted. Neighborhood interactions were weak, and concerns regarding safety often resulted in physical barriers rather than a social connection. Our response was to treat architecture itself as a social infrastructure. This philosophy led to some of the key principles as listed. The courtyard as a social infrastructure, visual connectivity across different levels, multiple access points, and visibility-driven safety. The project is organized around a central interactive courtyard, creating a common space visible and accessible by all major functions. Multiple access point connects the site to both the communities, allowing the building to become a shared destination rather than belonging to one single group. This is the ground pathway of our community market and the main building. And the blue point shows the vertical circulation that was required because of the bylaws given for the fire emergency staircase. Moving on the ground floor plan. This level forms the public heart of our project. Visitors arrive through a community gathering zone before entering the building. The community market works on the edge, which keeps up the already existing flow of Sunday market on that same road. The kitchen, dining area, kids zone are intentionally located here because they serve the highest number of daily users. At the center lies the courtyard, a primary gathering space. Coming to the first floor plan. The first floor focuses on the productive activities. Here we have the pulp making zone, brick workshop, lamp workshop, painting zone, plastic workshop, storage facilities, and other supporting services. Locating these functions around the courtyard allows the visibility into the making process, which is encouraging participation and learning. Rather than moving through the isolated corridors, users remain visually connected to activities occurring throughout the building. This strengthens awareness, participation, and community ownership. The second floor accommodates tailoring workshop, terrace access, and other support facilities. This level is particularly for the women and the youth. It is by providing dedicated space for skill development and entrepreneurship. There was a query posed in the review earlier. A decision was made to place the paper brick workshop on the first floor. That was because we divided it based on the function of functional segregation. This is because the final stage of the production requires a controlled drying environment with the consistent sunlight and ventilation. Therefore, it's on the terrace. Whereas the production there is a production on the first floor. This is to provide a better human comfortable environment. Also, the ground floor is clear of such activities because the ground floor is for highly public community functioning. Now, together, all these three levels creates a progression from public engagement to production and finally empowerment. This way, the architecture itself becomes a tool of building social and economic resilience. This is the stack of plan which brings us to our final form of our building. This form was selected because it strengthens community interaction, improves environmental performance, and creates a recognizable landscape for our neighborhood, giving our community the identity which it lacks. However, resilience alone cannot rely on philosophy. Every planning decision needs to be tested and validated. And therefore, we translated these design strategies into a performance-driven simulation. Adnan will guide you throughout all these quantitative analysis in environmental resilience.
Before we design anything, we ask a fundamental question. Which building form is most energy efficient for the Delhi's composite climate? So we run an iterative comparative analysis of multiple forms, testing each form for energy performance and solar radiation exposure. The V-shaped form with the lowest EPI of 163 kWh per meter square per year became our foundation. We further refine it into a G-shaped form. In this, courtyard is self-shaded, reducing solar load without any mechanical intervention. The radiation analysis revealed exactly where solar energy lands on this building. The roof received the highest amount of radiation, 900 to 1200 kWh per meter square per year. So we placed brick drawing panels and solar panels to convert this radiation into energy generation. The southwest facade received 600 to 900 kWh per meter square per year energy radiation. Our response was the terracotta jali and building integrated photovoltaic panels. Thermal analysis is conducted zone by zone, ensuring heat gain and heat loss is balanced. In building assembly, wall is designed with AAC block, CSEB block, and air gap, which reduces the heat gain. In roof assembly, terrazzo flooring with 0.7 VLT reflects incoming radiation. Polystyrene insulation prevents RCC slab absorbing solar heat. For glazing, multi-wall polycarbonated sheet with hollow air pockets create thermal barrier. We have also designed an earth air tunnel for peak summer temperature of 42 degrees Celsius to 45 degrees Celsius. The result of every design decision, form, envelope, jali, earth air tunnel, natural ventilation, reduces our EPI from baseline of 38 to 17 kWh per meter square per year, a 55% reduction from baseline. Lighting load are calculated through lumen method by integrating high efficacy fixtures and task-oriented light to achieve lowest lighting power density. Ventilation load are calculated as per IS code part 8, table 13. In equipment, energy efficient appliances are used to reduce equipment connected load. We achieve a significant reduction in lighting load by 57%, in ventilation 47%, and in equipment by 52%. Energy consumption versus energy generation graph shows we have surplus energy every month except January and December, where solar radiation is very low. For energy generation, we use a 36 kilowatt power solar plant with 115 modules, out of which 88 modules are placed on the roof and the remaining 27 modules are placed on the facade, which generates almost 45,000 kilowatt hour energy per year, achieving net zero status. The surplus energy of 9,000 kilowatt hour exported to the grid with net metering. We have selected 60 cell monoperk half-cut panels due to our irregular rooftop area and lower weight of the panel reduce the structural load on the building facade, as we are using this as BIPV. Hybrid inverter is used, ensuring uninterrupted operation during crisis, and 644 kilowatt hour battery provided for 72-hour disaster backup. Energy performance is only half the story. A building must also be healthy to live and work in. In health and well-being, CFD simulation confirms the complete ventilation journey. The interior courtyard velocities of 1 to 1.5 meter per second are well within the comfortable range. In interior spaces, air speed of 0.4 to 0.5 meter per second is achieved. Velocity difference between ground and roof creates stack effect, enables warm air extraction through high level openings. In daylight analysis, we achieve SDI of 76%. These exceed the LEED 2-point threshold. Mean illuminance of 9,731 lux reduces dependency on artificial lighting throughout the day. We have successfully reduced its annual sunlight exposure from 26 to 7 by implementing terracotta jali, which eliminates the glare risk. Passive cooling through foam and jali delivers 5,000 plus comfort hour. Remaining hours are covered by the earth air tunnel hybrid system. In waste management, workshop waste re-enter the production cycle as a raw material, closing the loop. Natural daylight ensures visual comfort. Earth air tunnel 3-layer filtration combined with zone-specific exhaust maintain clean air in every workshop. And a biflic courtyard landscape nurtures psychological well-being. Now, Web will carry forward.
Landscaping is not just about randomly planting trees. Landscaping is a very sophisticated process done by keeping in mind the aspects of psychology, ecology, and botany. The trees are chosen on the basis of aesthetics, maintenance, and low irrigation coefficient. That are Amaltas, Neem, and Peepal tree. Moving on to water performance. To reduce the water consumption demand in normal days and disaster days, we have used water efficient fixtures such as dual flush WCs, waterless urinals, low flow shower heads, and aerated taps, which reduce the unintentional water wastage. By using these fixtures, we have reduced the per capita consumption by 42% in normal days and 28% in disaster days. We have integrated rainwater harvesting in our design and grey water filtration to reduce the dependency on municipal water supply. And here we have the water circulation diagram showing the flow of water throughout the building. And this is the water balance table showing the monthly consumption and water sources monthly. Now for the structure, our building has used RCC structural system with M25 concrete and FE500 steel rebars. The building has 3 variations of columns and 2 variations of beams. The substructure is designed on the basis of soil bearing capacity of 150 km square. The type of foundation is isolated spread footing with clear cover of 50 mm. We have referred IS codes for concrete design, steel design, and seismic design. And we have used ETABS software for structural simulations. Now talking about the transition phase. After flood, 113 beds are to be placed in the building. This transition is going to take place under 24 hours with the help of all the workshop workers. And we can store 120 beds under the solar panel on terraces. Coming to the embodied carbon in the building, we can observe a reduction of 62% from the baseline. We have substituted baseline materials with lime-based terrazzo, polycarbonate sheets, PCC cement concrete, PPC cement concrete, recycled steel rebars, CACB blocks, ACC blocks, and fly ash blocks. We have optimized the material choice by keeping in mind the emission factor, U value, reflectance, and durability of the materials. For sourcing of material, we have reached out to the suppliers that are within the reach of 20 to 25 km of our site. Moving on to resilience and value proposition. By definition, resilience means the ability to adapt to changes. Our building is resilient in 5 aspects, that are architectural resilience. We can see how the building adapts to the changes during the flood by transforming itself into a flood shelter. Because of certain foldable walls, space becomes flexible for both functions. Disaster resilience. It shows how the structure is stable even under seismic loads, and the evacuation plans shows the efficient escape routes. Environmental resilience. It shows how the building contributes to the environment by reducing landfills and spreading awareness about sustainable living. Skill resilience. It shows how the people gain transferable employment skills from tailoring workshops. Community resilience. Our building model becomes resilient for the community by becoming an inclusive environment that promotes social well-being. Now coming to the next point, that are key achievement values of our project, which are as follows. 55% reduction in EPI, 62% reduction in embodied carbon, and 9,267 kilowatt hour per year surplus energy exported to Delhi grid, 6 crore capex and opex cost of building, 1.79 crore of combined annual profit from the workshop that we are doing in the building, and 56,74,291 litre per year municipal water demand has been reduced. Now concluding with the same question we started with. What if resilience was not just during the crisis, but during everyday life? This is the proposal we have. The rise, not just during the crisis, but community resilience in everyday life. Thank you.
Hello. Yeah. Thank you, team. You finished well in time. Let's hear the jury.
Congratulations for making it to finals. One of you mentioned when you know your why, you find your way. Can you again tell us the objective of your project?
The objective of our project was basically to enhance and enrich our community in all the aspects. Basically, our community, the two communities, are basically a one same community historically, but then they got divided because of the floods. And some of them left the floodlands and some did not. And together we wanted to enhance their present, because community resilience is not only about resilience during crisis time, it's about the overall development of a community. And therefore, that was our objective, to develop and give our community an identity. They are rag pickers and they don't really have, because we went and we had a on-ground experience and we just went into a puddle. as we stepped into the community. Though it was in between the main city, the entire atmosphere of that area had a very different air to it. And to enhance the entire thing, we felt was to overall enhance the entire community. Therefore, we provided them an economic development. We provided them a shelter. We provided them also a development during their crisis time, and that was our basic objective.
Understood. Okay. You mentioned about some trees and species to be chosen for the project. I saw some counting numbers of tree. What is the landscape percentage of the site from as percentage of landscape
413.
area? Yeah,
Our softscape is around 413 meter squares.
landscape area.
Yes.
No, percentage of the site
A
area.
percent of the site.
Tentative.
Our total site area is 9,080 meter square.
Okay.
Approximately it was 1/3 of the site.
400. You said 400.
So 900, 500, 25% around.
That's 900 is the site.
19,000. 1980. Yes.
What did say again? Landscape area.
1980. Sorry. Landscape area is 413 and our site area is 1980 meter square.
Okay, that doesn't look like, from the pictures you are showing, the rendered image you are showing.
That would be probably because most of the pavement used in the hardscape are perforated areas. So while rendering, those green area would be more prominent, I assume.
Okay. The last question. How are you actually working towards better indoor air quality over there? Delhi being Delhi, famous for air quality.
We have proposed earth air tunnel and there is a filtration process, a 3-type filtration in plenum chamber, and then when air is intact, there is a filtration, and when air is transferred through the pipe, there is one more filtration. And there is an exhaust which maintain the cross ventilations.
Okay, thank you.
I think a very good effort and a very good engagement with an urban issue. And I also appreciate your interpretation of what community resilience means, right? And I think my question or my concern in some sense still remains, and although you've tried to address it, is that when I see this shelter or this building as a community livelihood combined sort of space, I think it'll work very well. There's a lot of potential. There's a lot of need. I think you've done a very good analysis of the community needs. You have a good partner. My challenge still remains, I'm not able to visualize how the workshop space on the first floor will turn into a space where people can actually come and stay for a few days. Essentially because I feel that the kind of equipment that you need for pulping, this is not equipment that can be easily moved. And while I understand your preference for the first floor because of comfort level and access to the terrace, I'm still not able to visualize how this area will get transformed. It's not like school furniture that you can pick up and stack. This can be heavy machinery because you're probably going to put compression to make blocks, and they're going to be like machines to churn, requirement of water, etc. So that is something I'm still not able to visualize.
So these machines that are used for brick compression, they are movable, they are not fixed on the floor, and they can be moved by the workshop workers that are working here already. And we have also given that the whole transition is going to take place in 24 hours. These all machines are going to be transferred. The transformation is going to take 24 hours to complete. These machines will be moved to the storage and those beds will be transferred here. I know they're a bit heavy, but these workers are going to have to do it.
I would like to add on a point. In the chart we provided with, we have specified the machineries particularly and the dimensions of the machines, and they are more of like in a very compact size, and they can be like our model and then can be kept on the table. So it's not really heavy and very, it's basically a compact model. We have specifically chosen those model of machineries as specified in and it's a manual compression machineries are used.
So I'm sure you've done your homework, and I saw that you provided the details, and I really appreciate that. But you know, when you're actually evacuating, and so you may think that okay, we've given 24 hours, and there are workers who will evacuate. There's a certain cost of time, effort, re-establishment of that activity. And so, well, I'm not saying that you have to justify, but I'm just saying that what happens is that the challenges of, and also I think that you're probably underestimating the weight and the kind of size of the machinery and the kind of space required to move it and store it. It's not stackable. You'll have to think of all the passages that will have to move through, the kind of disruption it will cause. And since it is also linked to livelihood and a production cycle, to think of something that would disrupt that least would probably have been a more smoother transition from a workspace to a evacuation space. So that's just a thought. I'm sure you've given a lot to it, but
No, we get your point, sir. We get your point.
Yeah. I'll come down to the more fundamental form issue. You said that this form has come because of climate. Now, there are many reasons that you need a form for. Climate is definitely one of the reasons, no doubt, but function is also one of the reasons. And is there a way that function can take place and climate can be worked out? In the sense, suppose, let's say it's radiation. So you got to save it from radiation. There's a particular, facade that's having that problem. Then you kind of create a solution to that facade. The problem of design is to be able to find a solution to that problem. A function cannot be, that's not, you cannot, change a function, right? I mean, a toilet is a toilet is a toilet. A machine is a machine is a machine. It's going to operate. A bed, imagine the beds coming in. Is it the most efficient way of putting beds in the circular form? Is the next question. So all of these things also become as important in the design of a form. You're coming off the form from the angle of whatever sun radiation is okay, but that's not the only reason that you need to satisfy many other reasons. And so I think keep that in mind, that as a designer you will have to solve the problem. The function is also important. So in that sense, one feels you don't have to justify, but if you want to, you may answer.
The thing is, other than just the environmental aspect of this form, we also kept in mind that our community was very much not identified by neighborhoods, and they did not have an identity among itself. So we wanted to provide a building which can be a landmark of the neighborhood and give an identity, and the people actually engage with this building. And providing such form also brought in the people's interest to what's actually happening here, and would help us to improve the status and dignity of our community, along with it also having an interesting, like there's a community market running around. People would actually want to come and know what's happening, and then the sales would be on a better for this entire community. And Adnan, want to add something?
I think both run simultaneously, the form and the analysis of the climate. So
Yeah,
that's
because
why
this
we have
this
taken
thing
this
about
form.
what you just said, the lady just mentioned, it's a double-edged sword. If you're going to say that identity becomes form, because it's the activities, it's the community that needs to occupy. This can also be that the people don't want to enter this because it's such a formal-looking building. So it's a double-edged sword, and it's the activities that necessarily need to kind of create a sense of belonging especially for the community sense. Yeah, so that's one thing. The other is the tunnel. Really, did you research this? Because it has not been successful in India. Because I mean, PDEC system, passive downdraft evaporative, is the most simplest one, because there are many issues in the earth air tunnel issues, because you got to maintain the moisture, health issues. Also, very important is the cost of it in terms of the temperature drop that it gives you is just not workable. It has been, it's successful in a place like Ladakh where you have extreme temperatures. So you can go down, deep down, and extract the temperature of the earth back in. So there are, like in places like the West, in Canada and all, it's very successful. But it hasn't somehow taken off. And so I think you may want to kind of rethink the earth air tunnel. There are much more simpler systems available. Basically, you want fresh air. You want cool, fresh air. And PDEC system with simple coolers can also do that.
We thought after your comments that why we don't use PDEC system. The basic answer was that in PDEC system the relative humidity is it increases the humidity as it uses the water, but in earth air tunnel we are not using humidifier, so it is not increasing our humidity. It is in Delhi's composite climate, maintaining humidity is
Yeah, in those seasons you probably don't need anything.
no.
So there is the PDEC or most of these systems you need in peak heat. Rest of the weather, in fact, in dry weather, maybe in some parts of post rain, you may need for a month or two. But most, if you look at the larger climate issue, I mean, the weather chart, you will need the PDEC or any of these air cooling systems, any that is HVAC, mostly in certain months. And in places like this, you want to reduce costs. You don't want to make this like the haven for them, So you want to be careful in how you modulate your overall costs. So that was just one of the reasons. Many others, but generally I think you worked very hard, and I think you managed to come to this point, and I think it's a fantastic effort you put together. So congratulations for that.
Thank you, sir.
Thank you, jury members. Thank you, Team Solis. Yes. So, folks, that was our last presentation in the Community Resilience Shelter Division. Our esteemed jury panel has shown immense dedication for assessing this entities, and I want to thank them. Thank you for all the thoughtful assessment and comments, and I want to congratulate all the finalists. As the jury coordinator for this division, I have had the opportunity to see these teams submit their deliverables. They have done some incredible work. Forget that these teams have discovered a way to collaborate and do integrated design during the last 7 months. I think that it deserves a round of applause. Thank you so much to our jury members for your time, feedback, and guidance. And thank you to all our finalists for your participation. We will now take tea break in some time. This jury members will meet this evening and decide the winner and runner-ups. Who will it be? We have an exhibition called the Climatic Smart Innovation Exhibition, where you get to see innovative building products from the industry that addresses climate change. The exhibition is now open for you. Please proceed to the multiplex zone, which is about 5 minutes from here. And people who are online, stay tuned to our channel. At 6 p.m., watch the 10 exhibitors pitch their products in a bid to win the Climate Innovation Award. Until then, have a good evening. Before the jury begins their deliberations and before we proceed towards the tea, we have planned a short informal feedback session with the jury. This is an opportunity for all the finalists to interact with the jury members, ask questions, and receive feedbacks from their experience in the industry, as well as in the form of the review for your work today. We encourage you to use this time well, ask thoughtful questions, and make the most of jury's insights for next 20 minutes.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot.